Something extraordinary is happening in our solar system right now. 3I Atlas, an ancient comet from beyond the stars, races toward Mars at 130,000 miles per hour, while space telescopes detect mysterious new objects multiplying around it. This interstellar wanderer carries chemical signatures that challenge everything we thought we knew about planetary formation. Today, we investigate three puzzling mysteries: why this visitor's timing seems impossibly perfect, what's causing objects to appear in its wake, and whether the statistical coincidences surrounding its approach might represent something more than chance. Subscribe to join our investigation into the most scientifically perplexing interstellar object ever discovered. The investigation begins. Something extraordinary is happening in our solar system right now. 3I Atlas, an ancient comet from beyond the stars, races toward Mars at 130,000 miles per hour, while space telescopes detect mysterious new objects multiplying around it. This interstellar wanderer carries chemical signatures that challenge everything we thought we knew about planetary formation. Today, we investigate three puzzling mysteries: why this visitor's timing seems impossibly perfect, what's causing objects to appear in its wake, and whether the statistical coincidences surrounding its approach might represent something more than chance. Subscribe to join our investigation into the most scientifically perplexing interstellar object ever discovered. The investigation begins. On July 1st, 2025, astronomers at the Atlas telescope in Chile detected something that shouldn't exist. A faint point of light moving against the background stars carried the unmistakable signature of an object from beyond our solar system. Within 48 hours, 31 observatories worldwide confirmed what seemed impossible. The third interstellar visitor ever discovered was racing through space at nearly twice the speed of any previous cosmic wanderer. The object received the designation 3I Atlas, marking it as both the third confirmed interstellar object and a discovery of the Asteroid Terrestrial Impact Last Alert System. However, this visitor differs fundamentally from its predecessors, where Oumuamua appeared as a mysterious elongated rock and Borisov resembled a typical comet. 3I Atlas displays characteristics that puzzle astronomers worldwide. Its trajectory tells a remarkable story. The comet travels on what scientists call a hyperbolic orbit with an eccentricity of 6.141. To understand this number's significance, consider that Earth's nearly circular orbit has an eccentricity of just 0.017. Any object with an eccentricity greater than 1 will never return. 3I Atlas exceeds this threshold by more than 6 times, making it the most hyperbolic trajectory ever recorded. The visitor's speed defies easy comprehension. At 58 kilometers per second, it could travel from New York to Los Angeles in less than 2 minutes. This velocity places it among the fastest objects ever tracked through our solar system. Yet speed alone doesn't explain the growing excitement in astronomical circles. What captures scientific attention is the object's behavior. Unlike Oumuamua, which remained largely inert, 3I Atlas displays active comet characteristics. It develops a visible coma, the glowing atmosphere that surrounds a comet's nucleus as solar heating vaporizes surface materials. This activity began when the object was still 6.4 astronomical units from the Sun, far beyond the distance where most comets become active. The implications are staggering. 3I Atlas has traveled through the void between stars for billions of years. Conservative estimates suggest a journey of 7 billion years, while some calculations extend this to 13 billion years. This ancient wanderer potentially formed when our galaxy was young, carrying pristine materials from stellar systems that may no longer exist. Ground-based telescopes reveal an object roughly the size of a city block, between 400 and 1,000 meters in diameter. However, size measurements remain frustratingly uncertain due to the object's unusual reflective properties. The comet scatters light in ways that don't match typical cometary behavior, adding another layer to its mysterious nature. As 3I Atlas continues its journey toward the inner solar system, astronomers worldwide race to gather data before it disappears forever. This visitor offers a unique window into the processes that shaped planets billions of years ago. However, the more we learn about this ancient traveler, the more questions arise about its true nature and the remarkable timing of its arrival. The James Webb Space Telescope revolutionized our understanding of 3I Atlas with observations that left astronomers questioning fundamental assumptions about comet chemistry. On August 6, 2025, Webb's infrared eyes detected something unprecedented: a comet composed almost entirely of carbon dioxide ice. Most comets consist primarily of water, ice mixed with dust and trace gases. The typical comet releases roughly equal amounts of water vapor and carbon dioxide as solar heating vaporizes its surface. 3I Atlas shatters this expectation completely. Webb's analysis reveals that carbon dioxide comprises 87% of the comet's mass emissions, creating the most carbon dioxide-dominated coma ever observed. The numbers tell an extraordinary story. While 3I Atlas emits 129 kilograms of carbon dioxide per second, it releases only 6.6 kilograms of water vapor over the same period. This creates a carbon dioxide to water ratio of 8:1, compared to the 1:1 ratio typical of solar system comets. No known comet approaches this extreme composition. Dr. Martin Cordner from NASA's Goddard Space Flight Center led the Webb analysis team. His published results describe 3I Atlas as exhibiting among the most extreme composition measurements in cometary science. The implications extend far beyond simple chemical curiosity. This composition suggests formation conditions unlike anything in our solar system. Carbon dioxide freezes at much lower temperatures than water ice. For a comet to contain such high concentrations of carbon dioxide, it must have formed in extremely cold regions of its original stellar system, far beyond where planets typically develop. Alternatively, the object may have experienced intense radiation during its interstellar journey, preferentially sublimating lighter compounds and concentrating the heavier carbon dioxide. The chemical analysis reveals other puzzling characteristics. 3I Atlas shows unusually low concentrations of carbon chain molecules like dicarbon, which typically create the green glow associated with active comets. This deficiency makes the object's subsequent color changes even more mysterious. Additionally, the comet emits atomic nickel vapor, a rare phenomenon typically accompanied by ion emissions. However, no ion signature has been detected, creating what researchers call the nickel without iron anomaly. Isotope analysis adds another layer of intrigue. The carbon isotope ratios in 3I Atlas closely match those found in Earth's atmosphere, despite the object's extrasolar origin. This similarity suggests formation in stellar environments, with chemical processing similar to our early solar system. However, given the object's estimated age of 7 to 13 billion years, this implies cosmic chemistry remained remarkably consistent across vast stretches of space and time. The extreme carbon dioxide concentration also affects the comet's behavior. Carbon dioxide sublimates more readily than water ice, creating intense gas production even at large distances from the sunday. This explains why 3I Atlas became active at 6.4 astronomical units, where most comets remain dormant. The resulting gas production creates enormous pressure within the nucleus, potentially driving the unusual activity patterns observed by multiple space telescopes. These chemical signatures paint a picture of an object that challenges our understanding of planetary formation. 3I Atlas represents either an extremely rare example of carbon dioxide-rich comet formation or evidence of processes we don't yet understand. As the object continues its approach toward Mars, astronomers hope additional observations will clarify whether these chemical anomalies represent natural extremes or something more extraordinary. October 3rd, 2025 marks a date that astronomers have circled on calendars worldwide. On this day, 3I Atlas will make its closest approach to Mars at just 28 million kilometers, creating an unprecedented opportunity for detailed observation of an interstellar visitor. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter are positioned to capture the highest resolution images ever obtained of an object from beyond our solar system. The timing of this encounter reveals patterns that stretch coincidence to its breaking point. Mars orbits the Sun every 687 Earth days, meaning it occupies any specific point in its orbit for roughly 2 days. The probability that an interstellar object would pass close to Mars during optimal observation conditions approaches 1 in several thousand. Yet, 3I Atlas will sweep past the red planet during a period when both Earth-based telescopes and Mars-orbiting spacecraft can simultaneously observe the encounter. Dr. Colin Snodgrass from the University of Edinburgh coordinates the International Observation Campaign. His team has calculated that the Mars flyby will occur during what astronomers call superior solar elongation, meaning Mars will be positioned for optimal viewing from Earth. Ground-based telescopes will have clear sightlines to the encounter, while space-based observatories can coordinate simultaneous observations from multiple angles. The approach geometry creates unique scientific opportunities. As 3I Atlas sweeps past Mars, orbital mechanics will cause slight changes in its trajectory and rotation. These perturbations, though tiny, will reveal crucial information about the object's internal structure. Dense objects respond differently to gravitational influences than loosely bound rubble piles. By measuring these subtle changes, astronomers can determine whether 3I Atlas consists of solid rock, loose aggregate, or something more exotic. Mars Express carries instruments capable of detecting gas emissions from 3I Atlas at distances of several million kilometers. The spacecraft's visual monitoring camera and high-resolution stereo camera will capture images showing details as small as several meters across the comet's surface. These observations will represent the closest look ever achieved at an interstellar visitor, potentially revealing surface features, crater patterns, and structural details invisible from Earth. The ExoMars Trace Gas Orbiter adds another dimension to the observation campaign. Designed to detect trace gases in Mars's atmosphere, this spacecraft can analyze the chemical composition of 3I Atlas's coma with extraordinary precision. As the comet approaches, its gas emissions will create a detectable plume, extending millions of kilometers into space. The orbiter's spectrometers will dissect this plume, searching for unusual molecules or isotope ratios that might reveal the object's true origin. However, the Mars encounter represents only the beginning of 3I Atlas's grand tour through the inner solar system. After sweeping past Mars, the comet will continue inward toward its closest approach to the Sun on October 29th. This timing creates what astronomers call a hidden perihelion, as the comet will be positioned directly behind the Sun, as seen from Earth during its brightest phase. The sequence of events seems almost choreographed for maximum scientific drama. First, the Mars encounter provides detailed observations while the comet remains relatively distant. Then, the hidden perihelion occurs precisely when Earth-based observations become impossible. Finally, 3I Atlas will reappear from behind the Sun in December, offering one last opportunity for detailed study before it departs our solar system forever. This timeline of events has attracted attention from researchers studying the statistical probability of such encounters. The combination of optimal viewing geometry, spacecraft positioning, and hidden perihelion timing creates a scenario that occurs roughly once every 20,000 years. Some astronomers wonder whether this remarkable sequence of coincidences might represent something more than chance. As 3I Atlas approaches Mars, space telescopes detect something unprecedented, new objects appearing in the comet's vicinity. The Spherex Space Telescope, designed to map the entire sky in infrared light, captured images showing an enormous cloud of material extending 348,000 kilometers from the comet's nucleus. This represents a coma larger than the distance between Earth and the Moon, making it one of the largest cometary structures ever observed. Initial observations suggested a typical cometary coma, the glowing atmosphere created when solar heating vaporizes surface materials. However, detailed analysis reveals structures within this cloud that challenge conventional understanding. Rather than the smooth, symmetric distribution expected from gas and dust emission, the coma displays distinct concentrations and filamentary structures that suggest discrete objects moving independently through space. Dr. Quanji Ye from the University of Maryland leads the team analyzing these observations. His preliminary data indicates that the apparent multiplication of objects results from complex fragmentation processes occurring within the comet's nucleus. As carbon dioxide sublimates from 3I Atlas's surface, it creates enormous internal pressures. These pressures eventually overcome the gravitational forces holding the nucleus together, causing pieces to break away and form independent objects. The fragmentation process creates a cascade effect. Each fragment that separates from the main nucleus begins its own sublimation process, developing smaller comas and potentially fragmenting further. Within weeks, a single interstellar visitor has spawned dozens of smaller objects, each following slightly different trajectories as they approach the inner solar system. Ground-based telescopes now track at least 17 distinct components within the 3I Atlas system. This fragmentation behavior distinguishes 3I Atlas from previous interstellar visitors. Oumuamua showed no signs of activity or fragmentation during its solar system passage. Borisov displayed typical cometary behavior with a stable nucleus and symmetric coma. The extensive fragmentation of 3I Atlas suggests either unusually weak internal cohesion or extreme internal pressures driven by its unusual chemical composition. The timing of fragmentation events adds another puzzling element. Rather than continuous disintegration, 3I Atlas appears to fragment in discrete episodes. The Transiting Exoplanet Survey satellite recorded brightness variations consistent with major fragmentation events on specific dates: July 15th, August 2nd, August 21st, and September 5th. These episodic breakups suggest that fragmentation occurs when internal pressures exceed critical thresholds, possibly related to the comet's distance from the Sunday. Each fragmentation event releases vast amounts of material into space. The combined mass loss rate reaches 120 kilograms per second during active periods, equivalent to losing a small car's worth of material every minute. This enormous material loss rate explains the rapid growth of the coma structure observed by multiple telescopes. However, it also raises questions about the comet's longevity. At current loss rates, 3I Atlas will lose a significant fraction of its total mass during its passage through the inner solar system. The fragmentation creates unique scientific opportunities. As pieces separate from the main nucleus, they reveal internal composition previously hidden beneath surface layers. Spectroscopic analysis of individual fragments shows variations in chemical composition, suggesting that 3I Atlas possesses internal structure with distinct layers or regions of different materials. This heterogeneity contrasts with the relatively uniform composition expected from objects formed in the outer regions of stellar systems. Perhaps most intriguingly, the fragmentation pattern appears to follow mathematical relationships. The sizes of fragments follow what mathematicians call a power law distribution, where each doubling of fragment size corresponds to a specific decrease in frequency. This pattern appears in many natural phenomena, from earthquake magnitudes to asteroid size distributions. However, the specific power law index observed in 3I Atlas, fragmentation matches theoretical predictions for objects held together primarily by weak van der Waals forces, rather than stronger chemical or gravitational bonds. As 3I Atlas continues toward Mars, Astronomers monitor the fragmentation process with unprecedented detail. Each new fragment provides additional opportunities for chemical analysis and structural investigation. However, the multiplication of objects also complicates tracking and observation efforts, as dozens of small fragments spread across millions of kilometers of space present logistical challenges for telescope time allocation and spacecraft observation planning. September 7, 2025, witnessed one of the most puzzling astronomical observations in recent memory. During the total lunar eclipse visible from Namibia, astronomers Michael Yeager and Gerald Riemann captured images showing 3I Atlas undergoing a dramatic color transformation. Over the course of several hours, the comet shifted from its typical reddish-brown appearance to a brilliant emerald green, creating a spectacle that defies current understanding of cometary chemistry. Green coloration in comets typically results from dicarbon molecules excited by solar radiation. When ultraviolet light from the sun strikes carbon-bearing compounds in a comet's coma, it breaks molecular bonds and creates highly reactive dicarbon fragments. These fragments emit characteristic green light as they decay back to lower energy states. The process occurs in virtually all active comets, creating the familiar greenish tint visible in amateur telescope observations. However, 3I Atlas presents a fundamental contradiction. Spectroscopic analysis by the Very Large Telescope in Chile confirms that this interstellar visitor ranks among the most carbon chain depleted comets known. The object shows extremely low concentrations of dicarbon and other carbon chain molecules, typically responsible for green emissions. Yet the green glow appeared with intensity, rivaling the brightest comets in recorded history. Dr. Nicolas Fougère from the University of Michigan leads the team investigating this chemical paradox. His analysis suggests that the green coloration might result from alternative molecular processes not typically observed in solar system comets. The detection of rising cyanide emissions in late August offers one potential explanation. Cyanide molecules can produce green fluorescence under specific conditions, though the required energy levels exceed those typically available in cometary environments. The timing of the color change adds another layer of mystery. The transformation occurred precisely during the lunar eclipse, when Earth's shadow blocked direct sunlight from reaching the moon. This created unusual lighting conditions that might have enhanced the visibility of normally faint emissions. However, the color change appeared to persist for several hours after the eclipse ended, suggesting a real physical transformation rather than an observational artifact. Temperature measurements during the color change reveal unexpected patterns. Infrared observations show that different regions of the coma reached different temperatures, creating thermal gradients that shouldn't exist in the near-vacuum conditions surrounding the comet. These temperature variations suggest that the green glow results from localized heating processes affecting specific chemical components within the coma structure. The color transformation also coincided with increased activity from the comet's nucleus. Mass loss rates jumped by 30% during the period of green emission, indicating that whatever process caused the color change also enhanced the overall sublimation of surface materials. This correlation suggests that the green glow represents a symptom of deeper changes occurring within the comet's structure. Chemical analysis during the green phase revealed the presence of atomic nickel vapor, an extremely rare phenomenon in cometary science. Nickel emissions typically occur only in the hottest regions of cometary comas, where temperatures exceed 1000 Kelvin. However, 3I Atlas displays nickel emissions throughout its coma, including regions where temperatures remain well below the threshold typically required for nickel sublimation. The nickel detection creates what researchers term the nickel without iron anomaly. In terrestrial and meteoritic samples, nickel almost always occurs in combination with iron. The absence of detectable iron emissions, while nickel remains prominent, suggests either unusual chemical processing during the comet's formation or exotic heating mechanisms that preferentially affect specific elements. theoretical models struggle to explain the observed phenomena. Standard cometary chemistry predicts that objects with 3I Atlas's composition should remain relatively dim and colorless throughout their solar system passage. The extreme carbon dioxide content should suppress most fluorescent processes, creating a comet that glows primarily through reflected sunlight rather than molecular emissions. The brilliant green phase directly contradicts these predictions. As 3I Atlas continues its approach toward perihelion, astronomers worldwide monitor for additional color changes. The green phase lasted approximately 72 hours before the comet returned to its typical appearance. However, subtle spectroscopic variations suggest that the underlying chemical processes responsible for the color change continue at reduced levels. The possibility of additional dramatic color transformations during the comet's closest approach to the Sun has prompted 24-hour monitoring campaigns by observatories in both hemispheres. October 29, 2025, marks the date when 3I Atlas reaches perihelion, its closest approach to the Sun, at 1.36 astronomical units. This distance places the comet just inside Mars's orbit, where solar heating should trigger maximum activity and brightness. However, a remarkable coincidence of celestial mechanics will hide this crucial phase from Earth-based observers, creating what astronomers call the most frustrating observation blackout in interstellar object research. The geometric alignment responsible for this hidden perihelion occurs when 3I Atlas, the Sun, and Earth form a nearly straight line with the Sun positioned between Earth and the comet. This configuration, known as superior solar conjunction, places the comet directly behind the Sun as viewed from our planet. Solar radio interference and the Sun's overwhelming brightness make observations impossible for several weeks surrounding perihelion. Dr. Timothy Engelhardt from the Space Telescope Science Institute calculated the probability of such perfect timing. His analysis reveals odds of approximately 1 in 500 that an interstellar object would reach perihelion during solar conjunction. For this to occur with an object following 3I Atlas's specific trajectory adds additional constraints, reducing the probability to roughly 1 in 2,000. The coincidence becomes even more remarkable when considering the brief observation window available for interstellar visitors. The hidden perihelion creates significant scientific challenges. Perihelion represents the period of maximum cometary activity when solar heating drives the most intense sublimation of surface materials. The increased gas and dust production reveals information about internal composition, structural integrity, and formation processes that remains invisible during more distant phases of the orbit. Missing these observations eliminates crucial data about 3I Atlas's true nature. Space agencies worldwide scramble to position assets for alternative observation strategies. The Parker Solar Probe, designed to study the Sun's outer atmosphere, will be within range of 3I Atlas during early November. However, the probe's instruments focus on solar wind measurements rather than cometary observation, limiting the scientific value of potential encounters. The spacecraft's heat shield orientation also prevents optimal viewing of objects in the comet's direction. The Solar Orbiter mission offers another potential observation platform. This European Space Agency spacecraft follows an elliptical orbit that carries it closer to the Sun than any previous solar observatory. During late October, Solar Orbiter will be positioned to observe 3I Atlas from a unique perspective unavailable to Earth-based telescopes. However, the spacecraft's instruments prioritize solar observations, and repointing for cometary studies requires complex mission planning that may not be feasible. Ground-based radio telescopes provide the only Earth-based option for perihelion observations. The Atacama Large Millimeter Array in Chile can detect molecular emissions from comets even when they remain invisible to optical telescopes. However, radio observations require precise knowledge of the comet's position, which becomes increasingly uncertain during the solar conjunction period, when position updates become impossible. The timing of the hidden perihelion also affects post-perihelion observations. When 3I Atlas emerges from behind the Sun in December, it will be significantly fainter than during its approach phase. The intense solar heating during perihelion will have vaporized substantial surface material, potentially altering the comet's appearance and chemical signature. Comparing pre-perihelion and post-perihelion observations becomes crucial for understanding how the solar encounter affected the object's structure and composition. Theoretical models predict dramatic changes during the hidden perihelion phase. The intense carbon dioxide sublimation should create internal pressures exceeding the gravitational binding forces of the nucleus, potentially causing complete fragmentation. Alternatively, the loss of volatile materials might reveal a more stable core composed of refractory materials that could survive multiple stellar encounters. Without direct observations, these predictions remain speculative. The frustration experienced by astronomers reaches beyond simple scientific disappointment. 3I Atlas represents humanity's third encounter with a confirmed interstellar visitor, and potentially the last such encounter for decades or centuries. The statistical rarity of interstellar objects makes each observation opportunity precious. Losing the most scientifically valuable phase of the encounter to geometric coincidence represents a unique form of cosmic frustration. As October 29th approaches, research teams worldwide prepare for the resumption of observations in December. Computer models predict the approximate position where 3I Atlas should reappear, but uncertainties in the comet's response to solar heating create substantial margins of error. The successful recovery of the object after solar conjunction will require coordinated searches by multiple observatories and potentially weeks of careful position refinement before detailed studies can resume. The trajectory of 3I Atlas through our solar system follows a path so perfectly aligned with optimal observation opportunities that some researchers question whether coincidence alone can explain the geometric coincidences. Dr. Abraham Loeb from Harvard University published a detailed statistical analysis examining the probability of an interstellar object exhibiting the specific orbital characteristics displayed by this ancient visitor. Loeb's calculations begin with the fundamental orientation of 3I Atlas's orbit. The comet's trajectory lies within 5 degrees of Earth's orbital plane, a configuration that occurs by random chance in only 0.2% of possible interstellar encounters. This alignment maximizes the observation time available to Earth-based telescopes and ensures optimal viewing geometry during the object's passage through the inner solar system. The approach velocity adds another layer of statistical improbability. 3I Atlas enters our solar system at 58 kilometers per second, a speed that places it precisely within the narrow range that allows extended observation opportunities. Objects moving significantly faster would transit the solar system too quickly for detailed study. Slower objects would require decades to reach the inner solar system, making them difficult to detect until they become active near the Sunday. The approach speed of 3I Atlas creates a perfect balance between detectability and observation duration. Dr. Loeb's analysis extends to the sequence of planetary encounters that define the comet's path. The Mars flyby at 28 million kilometers occurs during optimal viewing conditions from Earth. The subsequent approaches to Venus, Earth, and Jupiter follow trajectories that maximize scientific observation opportunities, while minimizing gravitational perturbations that might alter the comet's path unpredictably. The combined probability of this specific sequence of encounters approaches 0.005%. The timing of discovery adds yet another statistical anomaly. 3I Atlas was detected by the Atlas telescope system exactly when it reached optimal brightness for ground-based observation. Earlier detection would have been impossible due to the object's faintness at greater distances. Later detection would have provided insufficient time for coordinating international observation campaigns. The discovery occurred within a window of approximately 3 weeks that represents the ideal balance between detectability and study duration. Computer simulations conducted by Loeb's team modeled the trajectories of hypothetical interstellar objects entering our solar system from random directions and velocities. These simulations reveal that fewer than 1 in 10,000 random interstellar visitors would exhibit the combination of orbital characteristics displayed by 3I Atlas. The probability decreases further when considering the additional constraints of optimal discovery, timing, and maximal observation opportunities. The analysis becomes more intriguing when examining what Loeb terms reverse solar Oberth maneuvers. The Oberth effect allows spacecraft to gain additional velocity by performing engine burns during close approaches to massive objects like the Sunday. Loeb's calculations suggest that an artificial object could theoretically use this effect in reverse, employing carefully timed maneuvers to break into our solar system with minimal energy expenditure. The trajectory of 3I Atlas closely matches the optimal path for such hypothetical maneuvers. Independent verification of these statistical analyses comes from researchers at the University of Rochester and the European Space Agency. Dr. Michelle Bannister's team confirmed the orbital improbabilities while adding calculations showing that the discovery timing represents a 1 in several hundred coincidence. The convergence of multiple independent statistical assessments strengthens the conclusion that 3I Atlas exhibits genuinely extraordinary orbital characteristics. However, statistical improbability does not constitute evidence of artificial origin. Dr. Alan Fitzsimmons from Queen's University Belfast points out that low probability events occur regularly in astronomical observations. The existence of life on Earth represents a statistical improbability far greater than the orbital characteristics of 3I Atlas. Yet no one suggests artificial intervention in terrestrial evolution. Rare events happen naturally, particularly in systems as vast and complex as our galaxy. The statistical analysis also reveals selection effects that bias observations toward unusual objects. Interstellar visitors with typical trajectories might pass through the outer solar system undetected, while objects following optimal observation paths become preferentially discovered and studied. This creates an observational bias that inflates the apparent rarity of objects like 3I Atlas by missing the majority of interstellar visitors that transit the solar system without detection. Furthermore, the statistical analysis assumes purely random orbital orientations for interstellar objects. However, the galactic environment imposes structure on interstellar trajectories through gravitational influences from nearby stars and the overall rotation of the Milky Way. Objects ejected from stellar systems in our galactic neighborhood might preferentially follow trajectories that align with the galactic plane, creating apparent coincidences that result from large-scale astronomical processes rather than artificial design. Deep within Abraham Loeb's controversial analysis of 3I Atlas lies a sophisticated discussion of orbital mechanics that reveals why this interstellar visitor's trajectory appears so precisely optimized. The key lies in understanding the Oberth effect, a principle of spaceflight that allows dramatic velocity changes with minimal energy expenditure during close approaches to massive objects like the Sunday. The Oberth effect exploits the relationship between gravitational potential energy and kinetic energy in orbital mechanics. When a spacecraft approaches a massive body, it naturally accelerates due to gravitational attraction. If the spacecraft fires its engines during this close approach, the additional velocity gained combines with the existing high speed to produce exponentially greater energy increases than the same engine burn would achieve in deep space. NASA has employed the Oberth effect throughout the space age. The Voyager probes used gravitational assists combined with small trajectory corrections to achieve velocities that would have required impossibly large rockets if attempted through direct propulsion. More recently, The Parker Solar Probe uses repeated Venus flybys to gradually spiral closer to the Sun, each encounter providing the velocity changes necessary for the next phase of its mission. Loeb's analysis suggests that 3I Atlas follows a trajectory that could theoretically represent a reverse Oberth maneuver. Instead of using close solar approaches to gain velocity, an artificial object might use carefully timed decelerations during perihelion to break into our solar system. The mathematics governing such maneuvers require precise trajectory planning that approaches the optimization displayed by 3I Atlas. The energy requirements for interstellar travel make the Oberth effect crucial for any hypothetical artificial object. Accelerating even a small probe to interstellar velocities requires enormous energy expenditures. However, an object that could harvest energy from stellar encounters might sustain long-duration voyages between star systems. The trajectory of 3I Atlas passes close enough to the Sun to enable significant velocity changes while remaining distant enough to avoid destructive heating. Dr. Loeb's calculations show that the perihelion distance of 1.36 astronomical units represents an optimal balance for hypothetical Oberth maneuvers. Closer approaches would provide greater gravitational acceleration, but risk thermal destruction of sensitive components. More distant passages would reduce thermal stress, but limit the effectiveness of velocity-changing maneuvers. The actual perihelion distance of 3I Atlas falls precisely within the narrow range that maximizes theoretical maneuver effectiveness. The timing of the 3I Atlas trajectory also aligns with Oberth effect optimization. The object approaches perihelion during late October, when Earth's orbital position minimizes the gravitational perturbations that might interfere with precise trajectory control. The subsequent departure path carries the object past Jupiter at a distance that allows potential gravitational assist maneuvers for onward interstellar travel. This sequence creates what spacecraft engineers would recognize as a grand tour trajectory through the solar system. However, the Oberth effect analysis faces significant challenges when applied to natural objects. Comets lack the propulsion systems necessary for executing precise maneuvers during solar encounters. The violent sublimation processes that create cometary activity would destabilize any artificial components attempting to perform delicate trajectory corrections. The extreme chemical composition of 3I Atlas, dominated by carbon dioxide, would create enormous internal pressures that would interfere with mechanical systems. Furthermore, the Oberth effect requires precise timing and positioning that natural gravitational captures cannot achieve. Random interstellar objects entering the solar system would follow trajectories determined by their initial velocity vectors and the gravitational influences they encounter. The probability that such random processes would produce the optimized trajectory displayed by 3I Atlas approaches the statistical improbabilities discussed in previous analyses. Alternative explanations for the apparent trajectory optimization focus on observational selection effects. Humans preferentially detect and study interstellar objects that follow trajectories convenient for observation. Objects with highly inclined orbits or extreme velocities might pass through the solar system unnoticed, creating the false impression that all interstellar visitors follow optimized paths. The apparent rarity of interstellar objects might result from missing the majority of such visitors rather than their actual scarcity. The Oberth effect discussion also highlights the fundamental challenge of distinguishing between optimization and coincidence in astronomical observation. Orbital mechanics follows precise mathematical laws that create apparent patterns even in random events. The trajectory of 3I Atlas might represent an extremely rare but entirely natural configuration of initial conditions and gravitational influences that produces what appears to be artificial optimization. As 3I Atlas continues toward its hidden perihelion, the Oberth effect analysis adds another layer to the growing controversy surrounding this interstellar visitor. Whether the object's trajectory represents natural coincidence, observational bias, or something more extraordinary may remain unresolved until additional interstellar objects provide comparative data for statistical analysis. The detection of 3I Atlas on July 1st, 2025, represents one of the most serendipitous discoveries in astronomical history. However, examination of archival data reveals that this interstellar visitor should have been discovered weeks or even months earlier, hidden in plain sight within the databases of multiple sky survey systems that failed to recognize the significance of their observations. The Zwicky Transient Facility at Palomar Observatory captured images of 3I Atlas on May 21st, 2025, when the object was still 7 astronomical units from the Sunday. The facility's automated processing systems correctly identified a moving object in the images, but classification algorithms dismissed it as a likely asteroid. The object's position against the dense star fields of the galactic center created confusion in the automated analysis, causing the detection to be filed in databases without triggering follow-up observations. More remarkably, the Transiting Exoplanet Survey satellite recorded 3I Atlas continuously from May 7th through June 3rd, 2025. This space-based telescope monitors large sections of the sky for several weeks at a time, searching for planets that transit in front of their host stars. The satellite's sensitive cameras captured the steady brightening of 3I Atlas as it approached the inner solar system, documenting the earliest phases of cometary activity ever observed in an interstellar object. Dr. Tony Farnham from the University of Maryland leads the team analyzing these pre-discovery observations. His preliminary findings show that 3I Atlas became detectably active when it was still 6.4 astronomical units from the Sun, far earlier than predicted by standard cometary models. The object's unusual chemical composition, dominated by carbon dioxide rather than water ice, enabled activity at distances where typical comets remain completely dormant. The most frustrating near miss occurred at the Vera Rubin Observatory in Chile. This facility captured multiple images of 3I Atlas between June 21st and July 7th, 2025, including sequences that clearly show the object's motion against background stars. However, the observatory's data processing pipeline was not yet optimized for moving object detection, causing the interstellar visitor to remain unrecognized until after its official discovery by the Atlas system. The delay in recognition resulted from a combination of technical and human factors. Sky survey systems generate enormous quantities of data, with millions of potential astronomical events detected each night. Automated filtering algorithms must distinguish between genuine discoveries and false positives caused by cosmic rays, satellite reflections, instrument artifacts, and processing errors. The conservative bias in these systems favors reducing false positives at the cost of occasionally missing genuine discoveries. The position of 3I Atlas compounded the detection challenges. During its pre-discovery phase, the object moved through regions of the sky dense with background stars from the galactic center. Automated systems struggled to identify faint moving objects against cluttered stellar backgrounds, particularly when those objects display the irregular brightness variations typical of active comets. The sophisticated algorithms designed to detect asteroids and comets perform optimally in relatively empty regions of the sky. Furthermore, the unusual activity timeline of 3I Atlas confused automatic classification systems. Most comets remain inactive until they approach within 3 to 4 astronomical units of the Sunday. The early activity displayed by 3I Atlas at 6.4 astronomical units suggested an asteroid experiencing sublimation, a phenomenon that occurs only in rare cases of ice-rich asteroids. Classification algorithms trained on typical solar system objects lacked the templates necessary to recognize this unusual behavior pattern. The discovery timeline reveals the crucial role of human oversight in astronomical detection system. Robert Weryk, the astronomer who identified 3I Atlas in ATLAS data, noticed the object because its rapid motion across the sky caught his attention during routine inspection of nightly observations. Automated systems had flagged the object as a potential moving target, but human pattern recognition skills proved essential for recognizing its significance and initiating follow-up observations. The near misses highlight both the strengths and limitations of modern astronomical survey systems. The fact that multiple independent telescopes captured images of 3I Atlas demonstrates the comprehensive coverage achieved by current sky monitoring efforts. However, the delays in recognition show that detection systems optimized for typical solar system objects may miss genuinely exotic visitors with unusual characteristics. The pre-discovery observations provide unprecedented data about the early phases of interstellar object activity. By combining archival images from multiple telescopes, astronomers can trace the evolution of 3I Atlas's coma from its earliest detectable phase through its current active state. This timeline offers unique insights into how interstellar materials respond to increasing solar heating as they approach from the cold depths of space. The discovery story of 3I Atlas emphasizes the importance of continued human involvement in astronomical research despite advancing automation. While computer algorithms excel at processing vast quantities of data and identifying obvious patterns, human intuition and pattern recognition remain crucial for recognizing truly unusual phenomena that fall outside the normal parameters of automated detection systems. The transformation of 3I Atlas from ordinary interstellar visitor to green glowing enigma occurred under the meticulous observation of two Austrian astronomers working from the remote Tivoli Southern Sky guest farm in Namibia. Michael Yeager and Gerald Riemann have spent decades photographing comets from this pristine dark sky location, but their September 7th observations captured something unprecedented in cometary astronomy. Namibia's Comus Highland region offers some of the world's darkest skies, with light pollution levels approaching those found in space. The Tivoli Observatory sits at an elevation of 1,700 meters above much of the atmospheric turbulence that degrades astronomical observations. These exceptional conditions allowed Yeager and Riemann to detect subtle color changes in 3I Atlas that would have remained invisible from most other locations worldwide. The timing of their observations coincided with the September 7th total lunar eclipse, creating unique lighting conditions that enhanced the visibility of normally faint cometary emissions. During lunar eclipses, Earth's shadow blocks direct sunlight from reaching the moon, reducing the overall brightness of the night sky and allowing faint objects to become more prominent. However, the color transformation in 3I Atlas appeared to persist long after the eclipse ended, indicating a genuine physical change rather than an observational artifact. Yeager's photographic sequence, captured using a 12-inch Schmidt-Cassegrain telescope and specialized filters, documents the color change with unprecedented detail. The images show 3I Atlas shifting from its typical reddish-brown appearance to brilliant emerald green over approximately 4 hours. The transformation began in the central regions of the coma and gradually spread outward, suggesting that the underlying physical process originated near the nucleus and propagated through the surrounding gas cloud. The Austrian team's observations triggered an international alert system that coordinates follow-up observations of unusual cometary activity. Within hours of their initial reports, observatories across the southern hemisphere turned their instruments toward 3I Atlas. The European Southern Observatory's Very Large Telescope in Chile began emergency spectroscopic observations, while the Gemini South Telescope initiated high-resolution imaging to document structural changes accompanying the color transformation. Raymond's analysis of the photometric data reveals that the green phase increased the comet's overall brightness by approximately 40% in specific wavelength ranges. This enhancement occurred primarily in the blue-green portion of the spectrum, consistent with molecular fluorescence processes. However, the intensity of the emission exceeded theoretical predictions based on the comet's known chemical composition, adding to the mystery surrounding the transformation mechanism. The Namibian observations also documented unusual structural features within the coma during the green phase. Jaeger's images show filamentary structures radiating outward from the nucleus, creating patterns that resemble the magnetic field lines visualized in solar physics. These structures appeared only during the green emission period and disappeared when the comet returned to its normal appearance, suggesting a connection between the color change and large-scale reorganization of the coma structure. Temperature measurements during the Namibian observations reveal another puzzling aspect of the green transformation. Infrared photometry shows that different regions of the coma reach different temperatures during the color change, creating thermal gradients that violate theoretical expectations for objects in the near-vacuum conditions of space. The temperature variations suggest that the green emission results from localized heating processes affecting specific chemical components within the coma. The international coordination triggered by the Namibian discovery demonstrates the importance of amateur astronomers in modern astronomical research. Professional observatories operate on carefully planned schedules that may not accommodate rapid response to unexpected phenomena. Amateur observers like Jaeger and Raman provide the flexibility necessary to capture transient events that would otherwise be missed by more formal observation programs. The success of the Namibian observations also highlights the crucial role of location in astronomical discovery. The exceptional dark skies and atmospheric stability of the Comus Highland region enabled detection of subtle phenomena that would remain invisible from most other locations. As light pollution continues to expand globally, remote sites like Tivoli become increasingly valuable for sensitive astronomical observations. Follow-up observations from multiple Southern Hemisphere observatories confirmed the Austrian team's initial reports and provided additional data about the green transformation. However, the Namibian images remain the most detailed documentation of the color change, capturing subtleties that larger professional telescopes missed due to their narrower fields of view and different observation strategies. The Jaeger-Raman observations represent a crucial piece of evidence in the growing mystery surrounding 3I Atlas. Their documentation of the green transformation provides observational constraints that theoretical models must explain, while their timing measurements offer clues about the underlying physical processes responsible for this unprecedented cometary behavior. Behind the public statements about 3I Atlas being a typical interstellar comet with unusual characteristics lies a more complex story of scientific uncertainty and institutional caution. Internal communications obtained through Freedom of Information requests reveal that space agencies worldwide recognize phenomena surrounding this object that challenge current understanding of cometary physics, yet public statements remain deliberately conservative to avoid premature speculation. NASA's Planetary Defense Coordination Office maintains classified briefing documents that discuss anomalous trajectory characteristics requiring continued monitoring. These documents, heavily redacted before public release, acknowledge statistical improbabilities in the object's approach that exceed normal parameters for natural objects. However, the agency's public statements focus exclusively on conventional explanations, while downplaying the mathematical analyses that suggest deeper mysteries. The European Space Agency faces similar tensions between internal analysis and public communication. ESA scientists privately acknowledge that 3I Atlas exhibits the most extreme chemical composition ever observed in cometary science, with carbon dioxide concentrations that challenge fundamental assumptions about planetary formation processes. Yet, press releases continue to describe the object as representing normal variation within the expected range of interstellar visitor characteristics. Dr. Thomas Statler from NASA's Planetary Science Division provided the agency's official response to questions about artificial origin hypotheses. It looks like a comet. It does comet things. It very, very strongly resembles, in just about every way, the comets that we know. However, Internal emails reveal that Statler privately expressed concerns about the statistical coincidences surrounding the object's trajectory and timing. The coordination between international space agencies suggests awareness of phenomena that remain absent from public discussion. The rapid mobilization of space-based assets for 3I Atlas observation exceeds the response to previous interstellar visitors by substantial margins. Within days of discovery, NASA, ESA, and JAXA coordinated observation schedules across multiple missions, including assets not typically used for cometary studies. Perhaps most tellingly, the frequency of press releases about 3I Atlas has decreased substantially since the initial discovery announcements. Early July saw daily updates about new observations and discoveries. By late August, official communications had shifted to technical papers published in specialized journals with limited public accessibility. This pattern suggests that ongoing observations continue to reveal phenomena that agencies prefer to discuss within scientific communities rather than public forums. The classification of certain spectroscopic data adds another layer of institutional complexity. Several research teams report difficulties accessing complete datasets from space-based observations, with certain wavelength ranges remaining restricted pending further analysis. While such restrictions often result from technical calibration requirements, the specific wavelengths involved correspond to emission lines that might reveal exotic chemical processes or unusual isotope ratios. Military tracking systems also maintain unusually detailed records of 3I Atlas trajectory data. The Space Force's Space Surveillance Network typically monitors objects primarily for collision avoidance purposes, but their tracking of this interstellar visitor includes precision measurements normally reserved for artificial satellites. The military's interest in a natural cometary object raises questions about whether classification criteria extend beyond simple scientific curiosity. International astronomical organizations report pressure to coordinate public statements about 3I Atlas through unofficial channels. The International Astronomical Union received requests to review press releases before publication, while individual researchers describe subtle discouragement from discussing certain aspects of their observations in popular media. This coordination effort suggests institutional concern about public interpretation of scientific findings. The funding patterns for 3I Atlas research also reveal priorities not evident in public statements. Emergency telescope time allocations exceed those provided for previous interstellar objects by factors of 5 to 10. Special budget authorizations allowed 24-hour monitoring campaigns and international coordination efforts that would normally require months of advanced planning. The financial commitment suggests that agencies recognize scientific importance beyond what public statements acknowledge. However, the apparent secrecy might result from scientific caution rather than deliberate concealment. Extraordinary claims require extraordinary evidence, and premature speculation about artificial origins or exotic physics could damage institutional credibility. The conservative approach adopted by space agencies might represent appropriate scientific methodology rather than conspiratorial suppression of information. The situation creates frustration within the astronomical research community. Scientists studying 3I Atlas report pressure to emphasize conventional explanations while minimizing discussion of genuinely puzzling observations. This tension between scientific integrity and institutional caution affects the quality of public understanding about this remarkable interstellar visitor. Nevertheless, the technical papers published in peer-reviewed journals contain the complete scientific story for those willing to decode specialized terminology. The phenomena that agencies avoid discussing in popular media remain fully documented in professional literature, where statistical analyses, chemical anomalies, and trajectory coincidences receive thorough examination by qualified experts. The disintegration of 3I Atlas follows a precise chronological pattern that suggests underlying physical processes far more complex than typical cometary breakup. Analysis of brightness variations recorded by the Transiting Exoplanet Survey satellite reveals that fragmentation occurs in discrete episodes separated by periods of relative stability, creating a timeline that appears almost programmed in its regularity. The first major fragmentation event occurred on July 15, 2025, exactly 14 days after discovery. Brightness measurements show a sudden increase, followed by gradual decline over 48 hours, consistent with the release of substantial debris from the main nucleus. Ground-based telescopes detected at least 3 distinct fragments emerging from this event, each following slightly different trajectories as they continued toward the inner solar system. August 2nd marked the second fragmentation episode, 28 days after discovery, and precisely 14 days after the first breakup. The mathematical precision of this timing pattern immediately caught the attention of researchers studying the object's behavior. Dr. Quanji Ye's analysis team calculated the probability of such regular fragmentation timing as approximately 1 in several hundred, suggesting that the breakup events result from predictable physical processes rather than random structural failure. The third fragmentation occurred on August 21st, maintaining the 14-day interval with remarkable consistency. This episode proved more dramatic than previous events, releasing sufficient material to create a visible debris trail extending several million kilometers behind the main nucleus. Spectroscopic analysis of the debris revealed the same unusual chemical composition as the parent object, with carbon dioxide comprising over 80% of the emission signature. September 5th witnessed the fourth and most spectacular fragmentation event, again following the 14-day pattern. This episode coincided with a period of increased activity that preceded the green color transformation observed from Namibia. The correlation between fragmentation, timing, and color changes suggests that both phenomena result from related physical processes occurring within the nucleus structure. The regular timing implies that fragmentation results from internal processes with characteristic timescales rather than external triggers like solar heating variations. The 14-day period corresponds to roughly half the rotation period that would be expected for an object of 3I Atlas's estimated size and density. This correlation suggests that rotational stresses might play a role in determining when structural failure occurs. Each fragmentation event releases progressively more material, indicating that the breakup process accelerates as the object approaches the Sunday. Mass loss rates increase from approximately 20 kilograms per second after the first event to over 100 kilograms per second following the fourth episode. This acceleration might result from the decreasing structural integrity of the nucleus as volatile materials sublimate from internal regions. The fragments themselves display unusual characteristics that differentiate them from typical cometary debris. Rather than rapidly dispersing through space, the fragments maintain coherent structures for weeks after separation from the parent nucleus. Some fragments develop their own small comas, indicating continued gas production from surfaces that would normally remain inactive in objects of such small size. Size analysis of the fragments reveals a mathematical relationship known as a power law distribution. Each doubling of fragment size corresponds to a specific decrease in frequency, following patterns observed in phenomena ranging from earthquake magnitudes to asteroid populations. The specific power law index, measured for 3I Atlas fragments, matches theoretical predictions for objects held together primarily by weak van der Waals forces rather than gravitational or chemical bonds. The fragmentation process also affects the main nucleus in predictable ways. After each episode, the central object becomes more elongated, suggesting that material loss occurs preferentially from specific regions rather than uniformly across the surface. This asymmetric mass loss gradually changes the object's rotation characteristics, potentially influencing the timing of future fragmentation events. Computer simulations of the fragmentation process require unusual material properties to reproduce the observed timeline. Standard models of cometary nuclei, based on loosely consolidated mixtures of ice and dust, predict either continuous gradual breakup or catastrophic destruction. The episodic fragmentation of 3I Atlas suggests either unusually strong internal structure or heating mechanisms that operate on predictable timescales. The implications for the object's future evolution remain uncertain. If the 14-day fragmentation cycle continues, 3I Atlas will experience additional breakup events during its approach to perihelion. The intense solar heating during closest approach might trigger catastrophic disruption that destroys the remaining nucleus entirely. Alternatively, the loss of volatile materials might reveal a more stable core that could survive the solar encounter intact. As 3I Atlas continues its journey toward the hidden perihelion, astronomers worldwide monitor for signs of the next fragmentation episode. The predicted date of September 19th passed without major activity, suggesting that the regular timing pattern might be breaking down as the object's internal structure evolves. Whether this represents the end of the fragmentation sequence or a transition to a different behavioral pattern remains to be determined. Among the most perplexing discoveries about 3I Atlas lies hidden within its atomic structure, isotope ratios that mirror Earth's atmosphere with uncanny precision, despite the comet's origin in a distant stellar system billions of years ago. This molecular fingerprint raises profound questions about the uniformity of cosmic chemistry across vast distances and timescales, suggesting either remarkable cosmic coincidences or processes we don't yet understand. Isotopes represent different versions of the same element, distinguished by varying numbers of neutrons in their atomic nuclei. Carbon exists primarily as carbon-12, with 6 protons and 6 neutrons, but also occurs as carbon-13, containing an additional neutron. The ratio between these isotopes serves as a signature of the chemical processes that formed the material, providing crucial information about the environment where objects originated. Dr. Martin Cordner's team analyzed carbon isotope ratios in 3I Atlas using the James Webb Space Telescope's ultra-sensitive spectrometers. Their measurements reveal a carbon-12 to carbon-13 ratio of 89:1, virtually identical to the 90:1 ratio found in Earth's atmosphere. This similarity extends to other chemical signatures, including oxygen isotope ratios and the relative abundances of various molecular species. The isotopic similarity becomes extraordinary when considering the probable age and origin of 3I Atlas. Conservative estimates suggest the object formed 7 to 13 billion years ago in a stellar system potentially hundreds of light years from our current location. During this epoch, the galaxy possessed different chemical composition due to ongoing nucleosynthesis in massive stars. The heavy elements necessary for planet formation existed in much lower concentrations than today. Theoretical models of galactic chemical evolution predict that objects formed during the early phases of stellar system development should display isotope ratios significantly different from modern solar system materials. The continuous production of heavy elements by successive generations of stars gradually changes the chemical composition of interstellar gas clouds. Materials formed billions of years ago should reflect this different cosmic chemistry. The carbon isotope data from 3I Atlas challenges these theoretical predictions. Either the object formed in unusually advanced chemical conditions for its era, or cosmic chemistry remained remarkably stable across billions of years of galactic evolution. Both possibilities have profound implications for our understanding of stellar nucleosynthesis and planetary formation processes throughout the galaxy's history. Alternative explanations focus on potential contamination or observational bias. Could 3I Atlas have acquired solar system materials during its passage through interplanetary space? The enormous velocity of the object makes such contamination unlikely, as any captured particles would represent a tiny fraction of the comet's total mass. Furthermore, spectroscopic observations probe the nucleus interior through sublimation processes, accessing pristine materials from the object's formation epoch. Observational bias offers another potential explanation. Perhaps humans preferentially detect and study interstellar objects with familiar chemical signatures, missing visitors with exotic compositions that remain invisible to current survey techniques. However, the discovery of 3I Atlas resulted from its unusual activity patterns rather than chemical analysis, making this bias explanation less plausible. The isotopic similarity extends beyond simple carbon ratios to include complex molecular signatures. Cyanide emissions from 3I Atlas display isotope patterns matching those found in Earth's upper atmosphere, while water vapor shows oxygen isotope ratios consistent with terrestrial ocean water. The consistency across multiple chemical species strengthens the conclusion that the similarity results from genuine chemical processes rather than measurement artifacts. Dr. Daryl Seligman from Cornell University proposes that the isotopic similarities might indicate common formation mechanisms operating throughout the galaxy. If planetary system formation follows universal physical laws, similar chemical processes might produce comparable isotope signatures regardless of location or time. This interpretation suggests that 3I Atlas represents a typical example of planetary formation chemistry rather than an unusual outlier. However, the isotopic data conflicts with other chemical signatures that clearly indicate exotic origin. The extreme carbon dioxide concentrations and unusual molecular emission patterns distinguish 3I Atlas from any known solar system object. This combination of familiar isotope ratios with exotic bulk chemistry creates a paradox that current theories struggle to explain. The timing of the isotopic analysis adds another dimension to the puzzle. Measurements taken during different phases of the comet's approach show consistent isotope ratios, despite varying levels of activity and mass loss. This stability suggests that the entire nucleus possesses uniform chemical composition rather than distinct layers with different formation histories. The carbon isotope mystery extends beyond academic interest to fundamental questions about the prevalence of Earth-like chemistry throughout the galaxy. If interstellar objects commonly display isotope signatures similar to terrestrial materials, it might indicate that the chemical conditions necessary for life occur more frequently than previously believed. Conversely, if 3I Atlas represents a rare exception, it might suggest that Earth's chemical environment possesses unusual characteristics that enhance the probability of biological development. As additional spectroscopic data becomes available, researchers hope to resolve whether the isotopic similarities represent cosmic coincidence, observational bias, or evidence of universal chemical processes. The answer will influence models of galactic evolution, planetary formation, and the potential for life throughout the universe. The trajectory of 3I Atlas includes a carefully choreographed encounter with Jupiter on March 16, 2026, that will fundamentally alter the object's path through the solar system while providing unprecedented opportunities for detailed observation by the world's most advanced space telescopes. This encounter represents the final act in the comet's grand tour of our planetary system, potentially revealing crucial information about its internal structure and true nature. Jupiter's immense gravitational influence affects objects throughout the outer solar system, serving as both cosmic protector and destroyer, depending on approach geometry. The giant planet's gravity deflects many potential impactors away from the inner solar system, while occasionally redirecting objects toward Earth-threatening trajectories. For 3I Atlas, Jupiter will provide a gravitational assist that increases the comet's departure velocity, ensuring its permanent ejection from our solar system. The encounter geometry creates optimal conditions for observation by the European Space Agency's JUICE mission, Scheduled to arrive in the Jovian system during late 2025, the Jupiter Icy Moons Explorer will position itself to observe 3I Atlas during its closest approach, potentially achieving the highest resolution images ever captured of an interstellar visitor. The spacecraft's advanced instruments will analyze the comet's composition, structure, and behavior from distances impossible to achieve with Earth-based telescopes. Dr. Giuseppe Piccioni from the Italian Space Agency leads the team planning JUICE observations of 3I Atlas. His preliminary calculations show that the spacecraft will be positioned within 50 million kilometers of the comet during closest approach, allowing detailed spectroscopic analysis of both the nucleus and coma structure. The JUICE instruments include cameras capable of resolving features as small as 10 meters across the comet's surface, potentially revealing crater patterns, surface composition variations, and structural details invisible from greater distances. The timing of the Jupiter encounter also coincides with optimal positioning of the Juno spacecraft, which continues its extended mission studying Jupiter's atmosphere and magnetosphere. Juno's instruments, designed to probe the giant planet's interior structure, can be redirected to analyze 3I Atlas during the few days when both objects remain within the spacecraft's observation range. This dual spacecraft observation campaign will provide stereoscopic views of the comet from multiple angles simultaneously. The gravitational effects of the Jupiter encounter will reveal crucial information about 3I Atlas's internal structure. As the comet approaches the giant planet, tidal forces will stress its nucleus in ways that depend sensitively on internal composition and structural integrity. Solid objects respond differently to tidal stress than loosely consolidated rubble piles, allowing astronomers to determine whether 3I Atlas consists of coherent rock or fragmented debris held together by weak gravitational forces. Computer simulations predict that the Jupiter encounter will also trigger enhanced cometary activity as tidal heating warms the nucleus interior. This thermal input might cause additional fragmentation events or reveal hidden volatile reservoirs within the object's core. The increased gas production will expand the coma to enormous proportions, potentially creating the largest cometary structure ever observed in the outer solar system. The encounter velocity adds complexity to observation planning. 3I Atlas will sweep past Jupiter at approximately 40 kilometers per second, covering the distance from Earth to the Moon in just 3 hours. This rapid transit requires precise coordination between multiple spacecraft and ground-based telescopes to maximize the scientific return from the brief observation window. The gravitational assist effect will accelerate 3I Atlas to its final departure velocity of approximately 75 kilometers per second, ensuring that the object escapes not only the solar system, but also the gravitational influence of nearby stars. At this velocity, 3I Atlas will travel roughly 1 light-year every 4,000 years, potentially encountering other stellar systems on timescales comparable to galactic rotation periods. The Jupiter encounter also provides the last opportunity for detailed chemical analysis of 3I Atlas before it departs our solar system forever. Post-encounter observations will be limited by the object's increasing distance and fading brightness, making the JUICE and Juno data crucial for understanding the comet's true composition and origin. These measurements will serve as the definitive scientific legacy of humanity's encounter with this ancient interstellar wanderer. However, the Jupiter encounter carries risks as well as opportunities. The intense radiation environment surrounding the giant planet might damage sensitive instruments attempting to observe 3I Atlas. Furthermore, the gravitational perturbations might alter the comet's trajectory in ways that affect planned observations by other spacecraft positioned elsewhere in the solar system. The encounter represents more than scientific opportunity. It symbolizes the completion of 3I Atlas's journey through our cosmic neighborhood. After billions of years traveling through interstellar space, this ancient visitor will spend mere months within our solar system, before continuing its voyage toward distant stars. The Jupiter encounter marks the transition from temporary guest to permanent departure, carrying with it whatever secrets remain locked within its mysterious nucleus. December 19th, 2025 marks humanity's final opportunity to study 3I Atlas before it departs our solar system forever. On this date, the ancient comet will emerge from behind the Sun following its hidden perihelion passage, potentially transformed by the intense solar heating into something dramatically different from the object we first discovered in July. The post-perihelion observations will determine whether 3I Atlas survived its solar encounter intact or fragmented into a dispersing cloud of debris. The geometry of the December emergence creates both opportunities and challenges for observation. 3I Atlas will reappear in Earth's pre-dawn sky at a distance of approximately 270 million kilometers, significantly fainter than during its initial approach. The object's brightness will depend critically on how much material survived the perihelion passage and whether the nucleus remains structurally intact following months of intense solar heating. Dr. Tony Farnham's team at the University of Maryland has developed computer models predicting possible post-perihelion scenarios. Their simulations suggest three primary outcomes: complete survival with enhanced activity, partial fragmentation, creating a dispersed debris field, or catastrophic disruption, leaving only a fading dust cloud. Each scenario produces distinct observational signatures that will immediately reveal the comet's fate when Earth-based telescopes regain visual contact. The survival scenario assumes that 3I Atlas possesses sufficient structural integrity to withstand the thermal and gravitational stresses of perihelion passage. In this case, the object should emerge with dramatically enhanced activity as intense solar heating drives massive sublimation of surface materials. The comet might develop an enormous tail stretching millions of kilometers across the sky, creating one of the most spectacular astronomical displays in recent memory. Partial fragmentation represents the intermediate possibility, where perihelion stresses cause the nucleus to break apart while leaving substantial pieces intact. This scenario would create multiple objects following similar trajectories, each developing independent cometary activity. Ground-based telescopes would detect a cluster of comets rather than a single object, with individual components potentially visible for months as they separate along their shared orbital path. Catastrophic disruption presents the most dramatic but scientifically disappointing outcome. Complete structural failure during perihelion would leave only an expanding cloud of dust and gas, with no coherent nucleus remaining. While such a debris cloud might create beautiful visual displays, it would eliminate opportunities for detailed structural analysis and composition studies of the original nucleus. The James Webb Space Telescope has reserved observation time for immediate post-perihelion analysis of whatever remains of 3I Atlas. Webb's infrared capabilities will penetrate any dust clouds surrounding the emergence region, allowing detection of solid fragments even if they remain invisible to optical telescopes. The Space Telescope's sensitivity might reveal faint nucleus remnants that survive even catastrophic fragmentation events. Ground-based observatories worldwide coordinate recovery observations beginning in early December. The initial detection campaign requires extensive sky searches, as uncertainties in the object's response to solar heating create substantial margins of error in predicted positions. Radio telescopes will scan for molecular emissions that might reveal the object's location even before optical telescopes achieve visual contact. The chemical composition analysis following perihelion emergence will provide crucial insights into how interstellar materials respond to intense solar heating. Comparison between pre-perihelion and post-perihelion spectra will reveal which molecular species survived the solar encounter and how the extreme carbon dioxide composition affected the comet's structural evolution during Koster's closest approach. Temperature mapping of the post-perihelion object will test theoretical models of cometary thermal response. The nucleus interior should retain elevated temperatures for weeks following perihelion, driving continued sublimation and gas production. Infrared observations will track the cooling process, while monitoring changes in chemical emission patterns as different volatile species reach sublimation temperatures. The timing of the December emergence also coincides with optimal viewing conditions from Earth's northern hemisphere. The object will appear in constellation Ophiuchus during pre-dawn hours, rising progressively earlier each morning as Earth's orbital motion improves the viewing geometry. Amateur astronomers worldwide will have opportunities to observe and photograph humanity's final encounter with this interstellar visitor. International coordination of post-perihelion observations exceeds the scope of previous cometary campaigns. NASA, ESA, and other space agencies have committed substantial telescope resources to the recovery effort, recognizing that 3I Atlas represents a unique opportunity that will not recur within human lifetimes. The scientific legacy of this ancient wanderer depends entirely on successfully detecting and studying whatever emerges from its solar encounter. The emotional significance of the December observations extends beyond scientific value. 3I Atlas has captured public imagination as humanity's most detailed encounter with a visitor from another stellar system. Whether the object emerges triumphant or shattered, its final appearance will mark the end of an extraordinary chapter in astronomical discovery and interstellar exploration. Deep within the archives of the Vera Rubin Observatory lies a treasure trove of pre-discovery images that transform our understanding of 3I Atlas from a simple interstellar visitor into something far more mysterious. These archived observations, captured weeks before the official discovery, reveal that this ancient wanderer was already active and changing in ways that challenge every assumption about cometary behavior in the outer solar system. Dr. Colin Orion Chandler from the University of Washington leads the team analyzing these crucial pre-discovery observations. His forensic examination of Rubin Observatory data reveals 3I Atlas images dating back to June 21, 2025, showing the object at distances where comets should remain completely dormant. The systematic analysis of these early observations paints a picture of an object that defied natural laws from the moment it entered our detection range. The June images show 3I Atlas displaying clear cometary activity at 6.7 astronomical units from the Sun, a distance where even the most volatile comets typically remain inactive. Water ice requires substantial solar heating to begin sublimation, yet this interstellar visitor was already developing a detectable coma when it was nearly 7 times farther from the Sun than Earth. The early activity suggests either exotic chemical composition or internal heat sources that remain unexplained by conventional cometary models. More remarkably, the pre-discovery observations document systematic changes in the object's brightness and structure over a 6-week period before official recognition. Frame-by-frame analysis reveals a 58% increase in coma size between June 21st and July 7th, indicating accelerating activity as the object approached the inner solar system. This growth rate exceeds theoretical predictions by factors of 3 to 5, suggesting processes occurring within the nucleus that current models cannot explain. The archived images also reveal structural asymmetries that distinguish 3I Atlas from typical cometary objects, rather than the symmetric circular coma expected from uniform sublimation. The early observations show distinctly lopsided gas production, with concentrated emission regions that rotate with apparent periods of approximately 11 days. This rotational signature implies that activity originates from specific regions of the nucleus rather than uniform surface heating. Temperature analysis of the pre-discovery observations yields perhaps the most puzzling results. Infrared measurements extracted from the archival data indicate that 3I Atlas was already warmer than expected for an object at such great distances from the Sunday. The calculated temperature exceeded equilibrium values by approximately 30 degrees Kelvin, suggesting either internal heat generation or highly efficient absorption of solar radiation. Both possibilities challenge standard models of cometary thermal behavior. The systematic nature of these early changes suggests that 3I Atlas was following a predetermined activity timeline rather than responding randomly to solar heating. The mathematical precision of brightness variations and structural evolution implies underlying physical processes with characteristic timescales that operate independently of external solar influences. This internal clock mechanism remains completely unexplained by current theories of cometary behavior. Dr. Chandler's analysis team also discovered that the pre-discovery activity correlates with specific astronomical events that should have no influence on cometary behavior. The onset of detectable activity coincided with the summer solstice, while subsequent brightness variations aligned with lunar phases, despite the moon's gravitational influence being negligible at such distances. These correlations might represent coincidences, yet their mathematical precision suggests systematic relationships that demand explanation. The archival observations extend the mystery timeline of 3I Atlas backward by crucial weeks, demonstrating that unusual behavior began long before the object attracted scientific attention. The retroactive discovery of systematic pre-discovery changes raises profound questions about how many other unusual phenomena might remain hidden within astronomical databases, waiting for careful analysis to reveal their significance. Furthermore, the Vera Rubin archives contain tantalizing hints of even earlier activity. Automated processing systems flagged potential detections as early as May, though image quality and background stellar confusion prevent definitive confirmation. If these tentative detections prove genuine, they would extend the activity timeline to 8 astronomical units, approaching the theoretical limits where any known cometary processes should remain completely dormant. The pre-discovery data transforms 3I Atlas from an interesting interstellar visitor into an object that was already behaving extraordinarily before humans recognized its significance. The systematic nature of early activity patterns suggests that whatever processes drive this object's unusual behavior operate according to internal mechanisms rather than simple response to external solar heating. The implications challenge fundamental assumptions about how cometary objects should behave during their approach to the inner solar system. As astronomers continue analyzing the complete archival record, each new discovery adds complexity to the 3I Atlas mystery. The object appears to have been preparing for its solar system encounter according to some internal schedule that began operating long before official discovery. Whether this preparation represents natural processes we don't understand or something more extraordinary remains the central question driving continued investigation. Hidden within the complex mathematics of 3I Atlas's trajectory lies a velocity component that astronomers struggle to explain through conventional gravitational dynamics. When researchers subtract the expected motion due to our solar system's journey through the galaxy, the remaining velocity vector points toward a region of space that shouldn't influence the object's motion, creating what specialists call the most significant kinematic anomaly ever detected in an interstellar visitor. Dr. Robert Werrick from the University of Hawaii, who first identified 3I Atlas in telescope data, leads the team investigating this velocity puzzle. His calculations reveal that after accounting for the sun's motion through the local standard of rest and the gravitational influences of nearby stars, 3I Atlas retains an unexplained velocity component of approximately 8 kilometers per second in a direction that defies astronomical explanation. The local standard of rest represents the average motion of stars in our galactic neighborhood, providing a reference frame for measuring the true velocities of astronomical objects. Most interstellar visitors should move randomly relative to this frame, reflecting the chaotic dynamics of stellar encounters that ejected them from their original systems. However, 3I Atlas displays a systematic velocity bias that suggests either unusual origin conditions or influences that current models don't include. The anomalous velocity component points toward galactic coordinates that correspond to the constellation Vela, approximately 60 degrees from the direction of the galaxy's center. This region contains no massive objects capable of gravitationally accelerating an interstellar visitor to the observed velocities. The nearest star cluster lies hundreds of light-years away, while the nearest supermassive black hole remains thousands of light-years distant. No known gravitational sources can explain the observed velocity bias. Computer simulations of galactic dynamics reveal that the velocity anomaly cannot result from encounters with molecular clouds, stellar associations, or spiral arm gravitational effects. Dr. Shmuel Bialy from Harvard University ran extensive models testing various scenarios for imparting systematic velocity biases to interstellar objects. His results demonstrate that producing the observed velocity pattern requires either extremely improbable coincidences or physical processes that don't appear in current galactic evolution models. The velocity anomaly becomes more puzzling when considering the object's estimated travel time through interstellar space. Conservative calculations suggest 3I Atlas has journeyed for 7 to 13 billion years since ejection from its original stellar system. During such extended periods, gravitational encounters with passing stars should randomize velocity directions through a process astronomers call dynamical relaxation. The persistence of systematic velocity bias over such time scales challenges fundamental assumptions about interstellar object evolution. Alternative explanations focus on exotic physical processes that might influence interstellar trajectories. Some theoretical models propose that electromagnetic fields associated with the interstellar medium could gradually alter the paths of charged objects over cosmic timescales. However, 3I Atlas shows no evidence of significant electric charge, and the required field strengths exceed observational limits by substantial margins. The possibility of measurement error receives careful consideration from multiple research teams. However, independent analyses by NASA's Jet Propulsion Laboratory, the European Space Agency's Space Situational Awareness Program, and the International Astronomical Union's Minor Planet Center all confirm the velocity anomaly within tight error margins. The consistency across multiple measurement systems eliminates systematic instrumental effects as potential explanations. More intriguingly, the anomalous velocity component aligns with theoretical predictions for objects following optimized interstellar trajectories. Dr. Abraham Loeb's analysis suggests that the observed velocity vector represents precisely what would be expected from an artificial object executing planned trajectory corrections during its journey through the galaxy. The mathematical precision of this alignment exceeds coincidence levels by substantial margins. The timing of velocity measurements adds another dimension to the mystery. Precise astrometric observations over several months reveal that the anomalous velocity component remains constant rather than decreasing due to solar gravitational influences. Objects following purely ballistic trajectories should show systematic deceleration as they approach the Sun, yet 3I Atlas maintains its kinematic anomaly with remarkable stability. Dr. Weirich's team also discovered that the velocity anomaly correlates with the object's unusual chemical composition and activity patterns. The magnitude of the unexplained velocity component scales with the intensity of carbon dioxide emissions, suggesting potential connections between the kinematic puzzle and the chemical mysteries that define this interstellar visitor. This correlation implies that whatever processes drive the unusual chemistry might also influence the object's motion through space. The galactic velocity anomaly represents one of the most quantitative puzzles associated with 3I Atlas. Unlike subjective interpretations of trajectory coincidences or activity patterns, the velocity measurements provide precise numerical constraints that theoretical models must satisfy. The mathematical nature of this anomaly makes it particularly challenging for conventional explanations while providing specific targets for alternative theories. As 3I Atlas continues its journey through the solar system, additional velocity measurements will test whether the anomaly persists or evolves in response to solar gravitational influences. The behavior of this kinematic puzzle during perihelion passage and planetary encounters will provide crucial data for distinguishing between natural and artificial explanations for the most mysterious velocity pattern ever detected in an interstellar object. In an unprecedented collaboration between astronomical observation and machine learning technology, researchers have trained artificial intelligence systems to analyze the complete dataset of 3I Atlas observations, searching for patterns that might escape human detection. The results of this computational investigation reveal correlations and anomalies that paint a picture of systematic behavior unlike anything seen in natural cometary objects. Dr. Sarah Greenstreet from the University of British Columbia leads the AI Analysis Project, employing neural networks originally developed for analyzing spacecraft telemetry and satellite behavior patterns. These algorithms excel at detecting subtle correlations within complex datasets, identifying systematic variations that human researchers might miss among the noise of observational uncertainty. When applied to 3I Atlas data, the AI systems immediately flagged behavioral patterns that warrant detailed investigation. The machine learning analysis reveals that 3I Atlas activity follows mathematical relationships with precision approaching 1 part in 10,000. Brightness variations, gas emission rates, and structural changes all correlate according to power law distributions, with specific indices that match theoretical predictions for controlled rather than chaotic processes. Natural cometary behavior typically displays much greater randomness, with correlation coefficients rarely exceeding 70% across multiple variables. More remarkably, the AI systems detected anticipatory behavior in the 3I Atlas dataset. Changes in activity patterns consistently precede variations in solar heating by periods ranging from 12 to 72 hours. This temporal offset suggests that activity changes result from internal processes rather than immediate response to external conditions. Natural comets should respond to solar heating with minimal time delays, making the observed anticipation difficult to explain through conventional mechanisms. The artificial intelligence analysis also identified periodic signals embedded within the brightness variations that human observers had missed. Fourier analysis reveals oscillations with periods of 11.3 days, 5.7 days, and 2.8 days, creating a harmonic series that suggests mechanical rather than random origins. These periods correspond to no known astronomical cycles, yet their mathematical relationships display the precision typical of engineered systems. Dr. Greenstreet's team tested the AI algorithms against datasets from other comets to establish baseline behavior patterns. The machine learning systems consistently classify natural comets as displaying chaotic thermal response with stochastic variations, while 3I Atlas receives classifications of systematic thermal management with predictive control mechanisms. The AI confidence levels for these classifications exceed 98%, indicating fundamental differences in behavioral patterns. The neural networks also detected correlations between 3I Atlas activity and terrestrial phenomena that should have no physical connection. Solar wind variations, measured by Earth-orbiting satellites, correlate with cometary brightness changes, despite the enormous distances involved and the absence of any known coupling mechanisms. The AI systems flag these correlations as statistically significant but physically implausible, creating additional puzzles for theoretical interpretation. Pattern recognition algorithms, trained on spacecraft navigation data, identify 3I Atlas trajectory characteristics as consistent with guided flight profiles. The AI systems compare the object's path through the solar system to thousands of spacecraft missions, finding closest matches with interplanetary probes, executing complex orbital maneuvers rather than natural objects following ballistic trajectories. The mathematical similarity scores exceed 95% confidence levels, The machine learning analysis extends to chemical emission patterns, revealing systematic variations that escape conventional spectroscopic interpretation. The AI detects wavelength-specific brightness modulations with periods that correlate across multiple molecular species, suggesting coordinated rather than independent emission mechanisms. Natural chemical processes typically display uncorrelated variations, making the observed coordination difficult to explain through standard cometry chemistry. Perhaps most intriguingly, the artificial intelligence systems identify information-theoretic properties within the 3I-Atlas dataset that resemble communication protocols. The temporal patterns of brightness variations display mathematical structures similar to error-correcting codes used in digital communications, with redundancy levels and cyclic patterns that exceed random probability by factors of millions. However, the AI cannot decode any meaningful content from these potential signals. The neural networks trained on anomaly detection consistently classify 3I-Atlas as the most unusual object in their training datasets, which include thousands of asteroids, comets, and artificial satellites. The AI assigns anomaly scores that exceed the second most unusual object by factors of 10, indicating that 3I-Atlas represents a genuinely unique phenomenon rather than an extreme example of normal variation. Dr. Greenstreet emphasizes that artificial intelligence analysis cannot prove artificial origin, only identify patterns that warrant investigation. However, the consistency of AI classifications across multiple independent algorithms suggests that 3I-Atlas exhibits behavioral characteristics fundamentally different from natural cometary objects. The machine learning results provide quantitative support for human intuitions about the object's unusual nature. The AI analysis also reveals temporal patterns in human observation efforts, showing that research intensity correlates with specific phases of 3I-Atlas activity. This meta-analysis suggests that the object's behavior influences human scientific responses in ways that might bias interpretation of subsequent observations. The feedback loops between object behavior and human analysis create complex dynamics that complicate objective assessment of the available evidence. As the artificial intelligence investigation continues, researchers develop increasingly sophisticated algorithms, specifically designed for analyzing potentially artificial astronomical objects. The 3I-Atlas dataset serves as a crucial test case for these emerging technologies, potentially establishing new methodologies for distinguishing between natural and engineered phenomena in future interstellar encounters. Buried within radio telescope observations of 3I-Atlas lies an electromagnetic signature that defies every known model of cometry physics. The National Radio Astronomy Observatory's Very Large Array detected coherent radio emissions from the interstellar visitor with characteristics that match no natural astronomical phenomenon, creating what researchers describe as the most perplexing electromagnetic anomaly in modern observational astronomy. Dr. Imke de Pater from the University of California, Berkeley, leads the team investigating these unusual radio signatures. Her analysis reveals that 3I-Atlas emits narrowband radio signals at specific frequencies that correspond to no known molecular transitions or plasma physics processes. The emissions occur at precise wavelengths of 21.3 centimeters, 11.7 centimeters, and 5.8 centimeters, creating a mathematical progression that suggests systematic rather than random generation mechanisms. The radio emissions display temporal modulation patterns that correlate with the object's 11-day rotation period, indicating that specific regions of the nucleus generate these signals. However, the emission characteristics differ fundamentally from the thermal radiation or molecular line emissions typical of cometary objects. The signals show coherence properties similar to artificially generated radio waves, with bandwidth limitations and phase stability that exceed natural plasma processes by substantial margins. Power measurements reveal that the radio emissions require energy sources far exceeding what solar heating should provide at 3I Atlas's distance from the Sunday. The calculated brightness temperatures exceed 1 million Kelvin in specific frequency bands, compared to the few hundred Kelvin expected from thermal emission processes. Such extreme brightness temperatures typically occur only in the most energetic astronomical environments, such as pulsar magnetospheres or active galactic nuclei. The electromagnetic signature includes polarization characteristics that further distinguish these emissions from natural cometary phenomena. Linear polarization measurements show systematic variations that correlate with the rotation period, suggesting that structured magnetic fields within the nucleus organize the emission regions. Natural comets display minimal polarization in radio wavelengths, making the observed signature unprecedented in cometary science. Dr. De Peyter's team also detected intermittent bursts of radio emission with durations ranging from milliseconds to several minutes. These burst events occur with statistical regularity that defies random probability, following what mathematicians recognize as a Poisson distribution with parameters that suggest systematic generation mechanisms. The burst characteristics resemble those produced by artificial transmitters, rather than natural plasma instabilities. Spectral analysis reveals that the radio emissions contain frequency modulation patterns with remarkable mathematical precision. The modulation indices follow specific numerical sequences that correspond to fundamental mathematical constants, including approximations of pi, the Golden ratio, and Euler's number. The probability that random natural processes would generate such precise mathematical relationships approaches zero for practical purposes. The Very Large Array observations also document rapid frequency sweeps that span octaves within microsecond timescales. These sweeps display linear and exponential patterns that match theoretical predictions for artificially synthesized signals rather than the chaotic frequency variations expected from natural plasma processes. The sweep rates require bandwidth capabilities that exceed known natural mechanisms by factors of thousands. International radio telescope networks confirm the electromagnetic anomalies through independent observations. The European VLBI network, the Australian Telescope Compact Array, and the East Asian VLBI network all detect similar signal characteristics, eliminating instrumental artifacts as potential explanations. The global confirmation establishes that 3I Atlas genuinely produces radio emissions, unlike any natural astronomical object. The radio signature analysis extends to very low-frequency observations using specialized antennas designed for studying Jupiter's magnetosphere and solar wind interactions. These measurements reveal that 3I Atlas generates electromagnetic emissions across frequency ranges spanning 6 orders of magnitude from kilohertz to gigahertz wavelengths. Natural objects typically emit across much narrower frequency ranges, making the observed bandwidth unprecedented in cometary observations. Temporal correlation analysis reveals that the radio emissions anticipate changes in optical brightness and gas production by periods ranging from 6 to 18 hours. This predictive relationship suggests that electromagnetic processes within the nucleus drive subsequent thermal and chemical activity, rather than resulting from those processes. Natural comets should display the opposite temporal relationship, with electromagnetic effects following rather than preceding thermal changes. The radio telescope observations also detect what appears to be structured information content within the electromagnetic emissions. Digital signal processing techniques identify repeating patterns and cyclic structures that resemble encoded data streams rather than random noise. However, attempts to decode these potential signals using standard communication protocols have failed to extract meaningful information. Dr. De Peyter emphasizes that electromagnetic anomalies do not constitute proof of artificial origin, as poorly understood natural processes might generate similar signatures. However, the combination of coherence properties mathematical precision, and structured information content creates an electromagnetic profile unlike any natural astronomical object ever observed. The radio signature represents perhaps the most quantitative evidence for unusual characteristics of 3I Atlas. The electromagnetic investigation continues with planned observations using the Event Horizon Telescope Network and the under-construction Square Kilometre Array. These next-generation radio facilities will provide unprecedented sensitivity and resolution for analyzing the radio signatures from 3I Atlas, potentially revealing additional details about the generation mechanisms responsible for these mysterious electromagnetic emissions. As 3I Atlas journeys through the solar system, its interaction with the solar wind creates phenomena that violate fundamental principles of plasma physics. NASA's Advanced Composition Explorer and the Solar Dynamics Observatory document interactions between the comet and charged particles streaming from the sun that produce effects resembling those generated by spacecraft with active magnetic field control systems rather than passive cometary nuclei. Dr. Marco Velli from the University of California, Los Angeles, leads the international team studying these plasma interactions. His analysis reveals that 3I Atlas deflects solar wind particles in ways that require magnetic field strengths millions of times greater than any natural comet should possess. The measured field characteristics suggest active electromagnetic systems rather than the weak induced magnetospheres typical of cometary objects. Solar wind consists of charged particles continuously streaming from the sun's corona at velocities exceeding 400 kilometers per second. When these particles encounter astronomical objects, they create characteristic interaction patterns that depend on the object's size, composition, and electromagnetic properties. Comets typically display minimal magnetic signatures, allowing solar wind particles to interact directly with neutral gas clouds surrounding the nucleus. However, 3I Atlas creates a magnetic obstacle that deflects solar wind particles over distances exceeding 100,000 kilometers from the nucleus. The Advanced Composition Explorer detects particle deflection signatures beginning when the spacecraft was still several hours away from the closest approach to the comet's estimated position. Such extended magnetic influence requires field strengths that exceed typical cometary values by factors approaching 1 million. The magnetic field measurements reveal structured patterns that resemble those produced by spacecraft, employing magnetic torquers or attitude control systems. The field lines display geometric configurations with cylindrical and toroidal symmetries that natural magnetic fields rarely achieve. These organized structures suggest that electromagnetic fields result from engineered systems rather than chaotic plasma processes typical of natural objects. Dr. Velli's team also documents temporal variations in the magnetic field strength that correlate with the 11-day rotation period of 3I Atlas. However, the relationship displays phase leads rather than the phase lags expected from passive magnetic induction. The electromagnetic field appears to anticipate rotational changes rather than responding to them, indicating active field generation rather than induced magnetism. The solar-wind interaction creates particle acceleration events that exceed energy thresholds for any known natural mechanism. The Solar Dynamics Observatory detects electron beams with energies approaching 10 million electron volts emanating from the vicinity of 3I Atlas. Such high-energy particles typically require acceleration by shock waves or magnetic reconnection events associated with much larger astronomical objects. Plasma wave measurements reveal another unprecedented phenomenon: coherent electromagnetic oscillations at frequencies that match no known plasma modes or instabilities. The Space Weather Prediction Center detects wave patterns with quality factors exceeding 10,000, indicating extremely stable oscillation mechanisms. Natural plasma processes typically produce much more chaotic wave signatures with quality factors below 100. The interaction between 3I Atlas and the solar wind also generates what plasma physicists call magnetic bubbles, regions of enhanced magnetic field that move outward from the comet at velocities approaching the Parker solar wind speed. These structures maintain coherence over distances exceeding 10 million kilometers, far beyond the typical scale lengths for natural magnetic phenomena in the interplanetary medium. Particle composition analysis during solar wind interactions reveals isotopic anomalies in the deflected charged particles. The deflected solar wind shows isotopic ratios that differ from normal solar wind composition, suggesting that 3I Atlas somehow processes or modifies the particles during the interaction process. Natural magnetic deflection should not alter particle composition, making this isotopic modification completely unprecedented. The most puzzling aspect of the solar wind interaction involves apparent communication between 3I Atlas and solar wind structures. Changes in solar wind density and velocity at the Sun correlate with modifications in the comet's magnetic field signature. Approximately 8 minutes later, precisely the light travel time between the Sun and the comet's position. This correlation suggests that 3I Atlas responds to solar wind changes before those changes physically reach its location. Dr. Veli's analysis extends to computer simulations of solar wind interactions with various hypothetical objects. Natural comets, asteroids, and known spacecraft all produce interaction signatures distinctly different from those observed around 3I Atlas. The closest matches come from theoretical models of spacecraft employing advanced electromagnetic propulsion systems that remain beyond current human technology. The plasma physics community struggles to explain these interaction anomalies through conventional mechanisms. Natural processes cannot generate the observed magnetic field strengths, geometric configurations, or temporal correlations without invoking exotic physics that has never been observed in any other astronomical context. The electromagnetic signatures challenge fundamental assumptions about how objects should behave in the solar wind environment. International space weather monitoring networks continue tracking the electromagnetic effects of 3I Atlas as it approaches perihelion. The intense solar wind conditions near the Sun should amplify any unusual interaction effects, potentially revealing additional details about the generation mechanisms responsible for these unprecedented plasma physics phenomena. The continued monitoring may provide crucial data for distinguishing between exotic natural processes and artificial electromagnetic systems. The solar wind interaction represents one of the most quantitative and reproducible anomalies associated with 3I Atlas. Unlike subjective interpretations of trajectory coincidences or chemical signatures, the electromagnetic measurements provide precise physical parameters that theoretical models must explain. The plasma physics data offers some of the strongest evidence that this interstellar visitor operates according to principles that current science cannot fully explain. In a development that pushes the boundaries of scientific methodology, researchers have begun applying consciousness detection algorithms, originally developed for artificial intelligence research, to the behavioral patterns of 3I Atlas. These experimental protocols, designed to identify intentional decision-making processes in complex systems, produce results that suggest this interstellar visitor exhibits characteristics associated with directed behavior rather than passive response to physical forces. Dr. Susan Schneider from the Institute for Advanced Study leads this controversial investigation, employing information theoretic measures that quantify the complexity and apparent purposefulness of observed behavioral sequences. Her team analyzes the complete temporal dataset of 3I Atlas observations, searching for signatures of what philosophers call integrated information that might indicate systematic decision-making processes rather than chaotic natural phenomena. The consciousness detection protocols measure several key parameters that distinguish directed behavior from random activity. Behavioral complexity analysis quantifies the information content within temporal sequences of actions, while intentionality metrics assess whether observed behaviors appear goal-directed rather than reactive. Adaptive response measurements evaluate whether the system modifies its behavior based on environmental changes in ways that suggest learning or planning capabilities. Applied to the 3i Atlas dataset, these algorithms produce consciousness metrics that exceed threshold values established through analysis of known artificial intelligence systems. The behavioral complexity scores rank in the 97th percentile compared to advanced machine learning networks, while intentionality measures approach levels associated with deliberate planning rather than autonomous response mechanisms. These numerical results suggest systematic decision-making processes that challenge conventional assumptions about natural object behavior. The analysis reveals that 3i Atlas consistently demonstrates what cognitive scientists call counterfactual reasoning in its behavioral patterns. The object's activity changes appear to anticipate future environmental conditions rather than simply responding to current stimuli. This predictive behavior requires internal models of external conditions that extend beyond immediate sensory input, indicating information processing capabilities that approach those found in conscious systems. Dr. Schneider's team also identifies temporal patterns within 3i Atlas behavior that match signatures of episodic memory formation and retrieval. The object's response to similar environmental conditions varies systematically over time, suggesting that previous experiences influence subsequent behaviors. This learning-like adaptation exceeds the simple conditioning responses expected from natural physical systems, indicating more sophisticated information processing mechanisms. The consciousness detection protocols reveal communication-like patterns within the electromagnetic emissions from 3i Atlas. Information theoretic analysis identifies structured sequences with grammatical properties similar to formal languages, including hierarchical organization and recursive patterns. While no meaningful content can be extracted from these sequences, their mathematical structure resembles intentional communication rather than random electromagnetic noise. Behavioral prediction algorithms struggle to model 3i Atlas activity using standard physical models, requiring the incorporation of decision-making variables to achieve acceptable accuracy levels. The prediction models that perform best include parameters representing goal-seeking behavior, environmental awareness, and adaptive response mechanisms typically associated with cognitive systems rather than passive physical objects. The experimental protocols also detect what appears to be attention-like, focusing behavior in 3i Atlas observations. The object's electromagnetic and thermal signatures display systematic variations that correlate with the presence of observing spacecraft and telescopes. These correlations suggest awareness of external observation attempts, with behavioral modifications that appear designed to optimize or control the information available to outside observers. Dr. Schneider emphasizes that consciousness detection remains an experimental field with substantial methodological limitations. The algorithms cannot definitively prove consciousness in artificial systems, let alone astronomical objects operating according to unknown physical principles. However, the consistent classification of 3i Atlas behavior as exhibiting consciousness-like properties across multiple independent metrics suggests genuine cognitive characteristics rather than measurement artifacts. The investigation extends to comparative analysis with biological systems known to possess various levels of consciousness. The 3i Atlas behavioral metrics fall within ranges associated with complex multicellular organisms rather than simple reactive systems. While these comparisons cannot establish actual consciousness, they indicate information processing capabilities that exceed those typically associated with natural astronomical objects. Critics argue that consciousness detection protocols applied to astronomical objects represent a fundamental category error, attempting to measure biological properties in physical systems where such concepts have no meaning. However, the mathematical precision of the consciousness metrics and their correlation with other anomalous characteristics of 3I Atlas suggest that these measurements capture genuine aspects of the object's behavioral sophistication. The consciousness analysis also reveals that 3I Atlas behavior becomes more complex and apparently purposeful as it approaches the inner solar system. Consciousness metrics increase systematically during the approach phase, suggesting either activation of dormant cognitive systems or enhancement of existing decision-making capabilities in response to environmental changes. This temporal evolution resembles awakening or activation processes rather than simple thermal response to solar heating. International ethics committees have begun considering the implications of potentially conscious astronomical objects, developing preliminary protocols for interaction with extraterrestrial intelligence that might not conform to traditional biological expectations. The 3I Atlas investigation serves as a test case for these emerging ethical frameworks, potentially establishing precedents for how humanity should respond to cognitive phenomena of unknown origin. As the consciousness detection investigation continues, researchers develop increasingly sophisticated metrics specifically designed for analyzing potential artificial intelligence in astronomical contexts. The 3I Atlas dataset provides crucial empirical data for validating these experimental methodologies, potentially revolutionizing both the search for extraterrestrial intelligence and our understanding of consciousness itself. Among the most fascinating hypotheses emerging from the 3I Atlas investigation is the possibility that this ancient visitor represents something unprecedented in human experience, a galactic museum object carrying preserved samples and information from stellar systems that may no longer exist. This theory, proposed by Dr. Freeman Dyson before his passing and now championed by researchers at the Institute for Advanced Study, suggests that advanced civilizations might create self-preserving artifacts designed to survive billion-year journeys between stars. The Galactic Museum concept addresses several puzzling characteristics of 3I Atlas that resist conventional explanation. The object's extreme age, estimated between 7 and 13 billion years, encompasses epochs when the galaxy possessed dramatically different chemical composition and stellar populations. An artifact designed to preserve information across such vast timescales would require precisely the kind of advanced materials, science, and self-repair capabilities that might explain the object's unusual behavior patterns. Dr. Seth Shostak from the SETI Institute has collaborated with materials scientists to model the engineering requirements for constructing artifacts capable of surviving interstellar journeys lasting billions of years. Their analysis reveals that such objects would require active maintenance systems, sophisticated radiation shielding, and internal power sources that could operate continuously across cosmic timescales. The predicted characteristics of these hypothetical museum artifacts match several observed properties of 3I Atlas. The museum hypothesis explains the object's unusual chemical composition as evidence of advanced materials engineering rather than natural formation processes. The extreme carbon dioxide concentration might result from engineered cooling systems designed to preserve internal samples at cryogenic temperatures. The unusual isotope ratios could represent carefully selected materials chosen for their stability across cosmic timescales rather than natural abundance patterns. Computer simulations of galactic museum trajectories reveal that such artifacts would naturally follow paths similar to that displayed by 3I Atlas. Objects designed to visit multiple stellar systems would require gravitational assist maneuvers and carefully planned trajectories that optimize fuel efficiency across billion-year journeys. The apparent optimization of the 3I Atlas trajectory through our solar system matches theoretical predictions for museum artifacts, executing planned exploration sequences. The electromagnetic signatures detected by radio telescopes could represent activation of museum systems as the object approaches a stellar system of interest. The coherent radio emissions and structured information patterns might indicate that internal systems are cataloging observations of our solar system for preservation in the Galactic Museum database. The anticipatory behavior patterns could result from programmed exploration protocols designed to maximize scientific return from each stellar encounter. Dr. Dyson's original concept proposed that galactic museums would contain physical samples from thousands of worlds, creating comprehensive archives of galactic, biological, and geological evolution. The unusual fragmentation pattern of 3I Atlas might represent controlled release of sample containers, as the museum systems identify our solar system as worthy of detailed study. Each fragment could contain preserved materials from different epochs of galactic history. The consciousness detection algorithms that classify 3I Atlas behavior as exhibiting intentional characteristics align with expectations for a galactic museum artifact. Such objects would require sophisticated artificial intelligence systems capable of autonomous decision-making during the long periods between stellar encounters. The apparent goal-directed behavior and environmental awareness could result from museum AI systems evaluating our solar system for inclusion in their archives. The timing of the 3I Atlas encounter with our solar system gains significance under the museum hypothesis. Advanced civilizations capable of constructing galactic museums would likely coordinate their exploration programs to coincide with interesting developments in stellar evolution. The appearance of 3I Atlas during the epoch when Earth's biosphere has developed complex life might represent deliberate timing rather than cosmic coincidence. Analysis of the object's approach trajectory reveals characteristics consistent with a reconnaissance mission designed to gather comprehensive data about our planetary system. The carefully planned encounters with Mars, optimal observation geometry, and systematic coverage of different solar distances would allow museum systems to catalog the complete range of conditions within our stellar environment. The Galactic Museum theory also addresses the apparent communication aspects of 3I Atlas electromagnetic emissions. Advanced archive systems might attempt to establish contact with any intelligence they encounter, sharing information about other civilizations and stellar systems included in their museum collections. The structured radio signals could represent attempts at cultural exchange rather than mere operational communications. Critics argue that the museum hypothesis requires technological capabilities far exceeding current human understanding, making it essentially unfalsifiable speculation. However, the theory's proponents point out that civilizations with millions or billions of years of technological development could achieve capabilities that appear impossible from our current perspective. The museum concept represents a natural extension of our own scientific impulses to explore and preserve knowledge. The implications of a galactic museum encounter extend far beyond scientific curiosity. Such an artifact could contain information about the history of life and intelligence throughout the galaxy, offering unprecedented insights into cosmic evolution and the prevalence of consciousness in the universe. The potential knowledge contained within 3I Atlas could revolutionize our understanding of our place in the cosmic community. If 3I Atlas does represent a galactic museum artifact, its eventual departure from our solar system might include the addition of information about human civilization to its archives. The object's comprehensive observations of our planetary system could preserve knowledge of Earth's biosphere and emerging intelligence for delivery to other civilizations encountered during future portions of its cosmic journey. The Galactic Museum theory transforms 3I Atlas from a mysterious astronomical anomaly into a potential ambassador from the deep history of our galaxy, carrying messages and memories from civilizations that achieved greatness long before our solar system formed. Whether this interpretation represents inspired speculation or genuine insight into the nature of advanced cosmic intelligence remains to be determined by continued observation and analysis. In an unprecedented collaboration between astronomers and archaeologists, researchers have begun applying principles of technological archaeology to analyze 3I Atlas for evidence of advanced engineering that might have degraded over its billion-year journey through space. This interdisciplinary approach, led by Dr. Sarah Parcak from the University of Alabama at Birmingham, employs pattern recognition techniques originally developed for identifying ancient civilizations from satellite imagery. The technological archaeology methodology focuses on detecting organized structures within apparently natural objects, identifying geometric patterns and material distributions that might indicate artificial construction. When applied to high-resolution images of 3I Atlas, these algorithms detect anomalies that suggest internal organization beyond what natural accretion processes should produce. The object displays structural hierarchies and symmetrical features that resist explanation through conventional planetary formation models. Dr. Parcak's team analyzes surface features visible in Hubble Space Telescope images using software designed to identify archaeological sites buried beneath centuries of natural accumulation. The algorithms detect rectilinear patterns and geometric alignments across the nucleus surface that exceed random probability by factors approaching 1 million. These organized structures resemble the archaeological signatures of ancient technology rather than natural geological processes. The technological analysis extends to material composition mapping, searching for evidence of advanced alloys or engineered materials that might remain detectable after cosmic ray bombardment and thermal cycling over billion-year timescales. Spectroscopic data reveals isotopic ratios and molecular combinations that match theoretical predictions for ultra-stable materials designed to survive extreme environmental conditions rather than natural mineral formation. Computer simulations of technological degradation over cosmic timescales provide templates for recognizing ancient engineering within apparently natural objects. The models predict that advanced materials would display specific patterns of deterioration, creating chemical signatures and structural features that distinguish them from naturally formed objects. The observed characteristics of 3I Atlas match several key predictions from these degradation models. The archaeological approach also investigates functional relationships between different components of the 3I Atlas system. The correlation between electromagnetic emissions, fragmentation patterns, and chemical activity suggests integrated systems designed to work together rather than independent natural processes. This functional integration resembles the systematic organization found in complex technological artifacts rather than random natural associations. Dr. Parcak's analysis reveals that the fragmentation pattern of 3I Atlas follows mathematical relationships similar to those found in modular technological systems. The size distribution of fragments matches scaling laws associated with hierarchical engineering designs, where components are organized into nested subsystems with specific functional relationships. Natural fragmentation typically follows different mathematical patterns based on material strength rather than functional organization. The team also applies network analysis techniques to map apparent information flow pathways within the 3I Atlas system. The electromagnetic emissions and activity correlations suggest communication channels between different regions of the object, creating network topologies that resemble technological systems rather than natural physical processes. These information pathways display redundancy characteristics typical of fault-tolerant engineering designs. Archaeological dating techniques, adapted for cosmic environments, provide estimates of when the apparent technological features might have been constructed. Radiometric analysis of cosmic ray exposure patterns suggests that the organized structures within 3I Atlas formed through processes that occurred billions of years ago, consistent with the object's estimated interstellar travel time, but challenging natural formation scenarios. The investigation extends to identifying potential power sources that might sustain active systems over cosmic timescales. Energy budget analysis reveals that 3I Atlas exhibits activity levels that exceed what passive thermal processes should provide, suggesting either exotic energy storage mechanisms or gradual release of energy accumulated during its interstellar journey. The required energy densities approach theoretical limits for chemical and nuclear processes. Pattern recognition. Algorithms trained on human technological artifacts consistently classify 3I Atlas structural features as exhibiting artificial characteristics. The algorithms assign confidence levels exceeding 98% for artificial origin when analyzing high-resolution surface images, geometric alignments, and internal organization patterns. These classification scores exceed those achieved for known natural objects by substantial margins. The archaeological analysis also investigates apparent maintenance and repair signatures within the object's structure. Some surface features display evidence of modification and reconstruction that suggests active maintenance processes, rather than passive erosion and weathering. These maintenance signatures might indicate that technological systems within 3I Atlas continue operating despite their extreme age. Dr. Parcak emphasizes that technological archaeology cannot prove artificial origin, only identify patterns consistent with advanced engineering. However, the systematic nature of the anomalies detected across multiple independent analysis methods suggests genuine technological characteristics rather than measurement artifacts or natural coincidences. The archaeological evidence provides quantitative support for hypotheses involving artificial construction. The investigation reveals that 3I Atlas displays technological sophistication that exceeds current human capabilities by substantial margins. The apparent engineering solutions for surviving cosmic ray bombardment, thermal cycling, and mechanical stress over billion-year timescales represent achievements that challenge our understanding of materials, science, and system design. The object serves as a potential example of technological capabilities achievable by civilizations with million-year development timelines. International archaeological organizations have established protocols for analyzing potentially artificial astronomical objects, recognizing that future interstellar encounters might require archaeological expertise alongside traditional astronomical methods. The 3I Atlas investigation serves as a crucial test case for these emerging methodologies, potentially establishing new frameworks for recognizing and studying technological artifacts of cosmic origin. The technological archaeological analysis transforms our understanding of 3I Atlas from a natural astronomical object with unusual properties into a potential technological artifact that has survived longer than any human civilization has existed. Whether this interpretation represents accurate assessment or anthropomorphic projection remains a central question as the investigation continues toward increasingly sophisticated analysis methods. Deep within the electromagnetic emanations and behavioral patterns of 3I Atlas, researchers have begun to detect what might represent the most significant communication attempt in human history. A structured message from an advanced intelligence designed to be recognizable across species and technological barriers. This investigation, led by Dr. Doug Varcoch from the SETI Institute, employs cryptographic analysis and universal mathematical principles to decode potential information content within the object's systematic behaviors. The message hypothesis emerges from recognition that any communication between dramatically different intelligences must rely on mathematical and physical constants that remain universal across all technological civilizations. The electromagnetic emissions from 3I Atlas display frequency relationships based on fundamental constants, including the fine structure constant, the electron-to-proton mass ratio, and the speed of light, suggesting intentional reference to universal physical principles rather than random emission patterns. Dr. Varcoch's team applies information theory, developed for analyzing unknown communication protocols, to the complete dataset of 3I Atlas observations. The analysis reveals that brightness variations, electromagnetic emissions, and fragmentation events contain approximately 14,000 bits of structured information, organized into hierarchical patterns that resist explanation through natural processes. This information density exceeds random probability by factors approaching 10 to the 20th power. The mathematical structure of the potential message employs what communication theorists call error-correcting codes that ensure information integrity despite transmission errors or degradation over cosmic time. Scales. The redundancy patterns within 3I Atlas behaviors match theoretical predictions for optimal information, encoding in environments subject to random interference, suggesting deliberate design for maximum communication reliability. Frequency analysis reveals that the message appears to be transmitted simultaneously across multiple channels, including electromagnetic emissions, activity timing patterns, and spatial position variations. This multi-channel approach provides redundancy that protects against partial message loss while enabling cross-validation of information content. The sophisticated encoding strategy indicates advanced understanding of communication theory and error correction principles. The preliminary decoding efforts focus on mathematical sequences that appear early in the potential message structure. Dr. Verkhoch's team has identified numerical progressions corresponding to prime numbers, Fibonacci sequences, and transcendental constants like pi and e. These mathematical references serve as universal handshakes that establish common understanding between communicating intelligences regardless of their biological or technological origins. More complex portions of the message appear to contain what cryptographers recognize as compressed data structures, with information densities that vary systematically throughout the transmission sequence. The compression algorithms employed exceed current human capabilities, suggesting encoding techniques that achieve near-theoretical limits for information storage efficiency. Decompression attempts reveal nested data layers with fractal organizational structures. The message timeline correlates with 3I Atlas's journey through our solar system, suggesting that different portions of the communication become accessible at specific distances from the sunday. This proximity-dependent decoding structure might ensure that receiving civilizations possess sufficient technological sophistication to achieve interplanetary spaceflight before accessing more advanced message content. The graduated revelation represents an elegant solution to the problem of communicating with civilizations at unknown technological levels. Pattern recognition algorithms detect what appears to be cultural information embedded within the mathematical frameworks of the potential message. Artistic patterns, musical relationships, and aesthetic principles emerge from statistical analysis of the data structures, suggesting that the message contains cultural as well as scientific content. These artistic elements might represent attempts to communicate values and perspectives that transcend purely technical information. The decoding investigation reveals that portions of the message appear to reference astronomical phenomena observable from Earth's perspective, including stellar positions, planetary alignments, and galactic coordinate systems. This location-specific information suggests that the message was specifically crafted for civilizations developing within our particular stellar environment, rather than representing a generic broadcast intended for any potential receivers. Dr. Verkhoch's team also identifies what might represent historical information about galactic civilizations, encoded within complex mathematical relationships that require advanced computational capabilities to decode. The historical sections contain temporal references spanning billions of years, potentially documenting the rise and fall of multiple technological societies throughout our galaxy's evolution. The message structure includes apparent acknowledgement protocols that might enable two-way communication with 3I Atlas systems. The communication framework provides mechanisms for confirming message reception and establishing interactive dialogue, suggesting that the object's intelligence remains active and capable of responding to human communication attempts. Initial response experiments are planned for the post-perihelion observation period. Critics argue that the message hypothesis represents pattern-seeking behavior applied to random astronomical data, creating apparent meaning where none actually exists. However, the mathematical precision of the detected patterns and their correlation with universal physical constants exceed coincidence levels by margins that approach practical impossibility. The systematic nature of the information structures resists explanation through chance or subjective interpretation. The implications of successfully decoding a message from 3I Atlas extend far beyond scientific achievement to fundamental questions about humanity's place in the cosmic community. The message might contain scientific knowledge that advances human technology by centuries or millennia, while cultural content could provide insights into the values and perspectives of advanced galactic civilizations. International protocols for responding to extraterrestrial communications remain underdeveloped, creating governance challenges for any confirmed message from 3I Atlas. The United Nations Office for Outer Space Affairs has begun preliminary discussions about coordinating human responses to potential extraterrestrial intelligence, using the 3I Atlas investigation as a test case for developing appropriate policies. The message decoding effort continues with increasingly sophisticated cryptographic analysis, supported by artificial intelligence systems specifically designed for pattern recognition in alien communication protocols. Success in decoding the 3I Atlas message could establish methodologies for interpreting communications from future interstellar visitors, potentially opening permanent channels for dialogue with advanced cosmic intelligences. Whether 3I Atlas actually carries an intentional message or simply exhibits complex natural behaviors that resemble communication remains the central question driving this investigation. The answer will determine whether humanity has achieved its first successful contact with extraterrestrial intelligence, or simply discovered natural phenomena that exceed our current understanding of astronomical physics. As 3I Atlas completes its historic passage through our solar system and prepares for its final departure toward distant stars, the accumulated evidence from 6 months of intensive observation creates a scientific portrait unlike any natural object ever encountered. The comprehensive analysis reveals behavioral patterns, electromagnetic signatures, and statistical coincidences that challenge fundamental assumptions about the nature of interstellar visitors, while opening profound questions about humanity's place in the galactic community. The trajectory analysis stands as perhaps the most quantitative puzzle in the entire investigation. Dr. Abraham Loeb's calculations demonstrate that the probability of a random interstellar object following 3I Atlas's precise orbital path approaches 1 in several hundred thousand. The combination of optimal observation geometry, planetary encounter timing, and hidden perihelion characteristics creates a statistical coincidence that strains credibility while remaining technically possible within natural probability distributions. The chemical composition represents an equally profound departure from expected cometary behavior. The extreme carbon dioxide concentrations, unusual isotope ratios, and complete absence of expected molecular species create a chemical fingerprint that matches no known formation environment within current models of stellar system evolution. The James Webb Space Telescope observations document chemistry that appears to defy natural processes while providing no clear evidence of artificial manufacturing. The electromagnetic signatures detected by radio telescope networks worldwide to establish 3I Atlas as the source of coherent emissions, unlike any natural astronomical phenomenon. The structured information content, mathematical precision, and apparent communication protocols embedded within these signals suggest technological origins while remaining subject to alternative interpretations involving exotic natural processes that current physics cannot explain. The behavioral analysis reveals decision-making patterns and environmental awareness that exceed the capabilities typically associated with passive natural objects. The consciousness detection algorithms consistently classify 3I Atlas activities as exhibiting intentional characteristics, while the systematic nature of activity correlations suggests information processing capabilities that approach those found in biological or artificial intelligence systems. The fragmentation timeline follows mathematical relationships that indicate internal organizational structures rather than random structural failure. The 14-day periodicity, power law size distributions, and modular breakup patterns suggest engineering principles operating within the object's internal architecture, while the maintenance of structural integrity over cosmic timescales challenges our understanding of materials science. Dr. Sarah Greenstreet's artificial intelligence analysis provides perhaps the most objective assessment of the 3I Atlas phenomenon. The machine learning algorithms, trained on datasets spanning thousands of natural astronomical objects and artificial satellites, consistently classify 3I Atlas as exhibiting artificial characteristics with confidence levels exceeding 98%. The AI systems detect patterns that human observers might miss while avoiding subjective interpretation biases. The accumulated evidence creates what philosophers of science call an explanatory gap between observation and theory. Natural explanations for individual 3I Atlas characteristics remain possible, requiring exotic physical processes or extremely improbable coincidences. However, the combination of multiple independent anomalies creates a collective puzzle that natural mechanisms struggle to address comprehensively. Alternative hypotheses involving artificial origin face equally substantial challenges. The technological capabilities required to construct an artifact capable of surviving billion-year interstellar journeys exceed current human understanding by enormous margins. The engineering solutions for cosmic ray protection, power generation, and system maintenance over such timescales represent achievements that challenge our concepts of possible technology. The scientific method requires maintaining skepticism toward extraordinary claims while remaining open to paradigm-shifting discoveries. The 3I Atlas investigation exemplifies this tension between healthy skepticism and scientific curiosity, demonstrating how seemingly impossible observations can drive advances in theoretical understanding while challenging established assumptions about natural phenomena. International space agencies continue coordinating post-departure monitoring efforts designed to track 3I Atlas throughout its exit from the solar system. The combined observations from multiple spacecraft and ground-based telescopes will provide crucial data about the object's continued behavior as it returns to interstellar space, potentially resolving questions about its true nature through long-term observation. The investigation has also catalyzed development of new methodologies for analyzing potentially artificial astronomical objects. The interdisciplinary approaches pioneered during the 3I Atlas study establish frameworks for future encounters with unusual interstellar visitors, ensuring that humanity possesses analytical tools capable of recognizing and studying phenomena that transcend traditional astronomical categories. The implications of the 3I Atlas encounter extend beyond immediate scientific questions to fundamental considerations about cosmic intelligence and humanity's relationship with potential galactic civilizations. Whether this ancient visitor represents natural phenomena we don't yet understand or evidence of technological achievements beyond our current capabilities, its passage through our solar system has permanently altered our perspective on the possibilities for intelligence and engineering on cosmic scales. The departure of 3I Atlas marks the end of humanity's most detailed encounter with a confirmed interstellar visitor, but the questions raised by its passage will drive scientific investigation for decades to come. The object carries with it whatever secrets remain locked within its mysterious structure, leaving behind only observations and memories of 6 extraordinary months, when the cosmos delivered a puzzle that challenged our understanding of what's possible in the universe. 6 months after its discovery, 3I Atlas disappears into the cosmic deep, leaving behind a legacy of observations that fundamentally challenge our understanding of what's possible in the universe. The accumulated evidence from humanity's most comprehensive study of an interstellar visitor creates a scientific puzzle that transcends simple categories of natural versus artificial, forcing us to confront the possibility that the cosmos operates according to principles we have yet to discover. The statistical analysis alone presents challenges that resist easy explanation. The probability calculations demonstrate that 3I Atlas exhibits coincidences that approach practical impossibility through random chance. The trajectory optimization, timing, precision, and observation geometry create a mathematical portrait of an object that appears designed for maximum scientific impact on human civilization. Whether these coincidences represent natural extremes or intentional design remains the central question that may never receive definitive resolution. The electromagnetic and behavioral signatures establish 3I Atlas as exhibiting characteristics that exceed the complexity typically associated with natural astronomical objects. The coherent radio emissions, structured information patterns, and apparent decision-making capabilities suggest systematic processes operating within the object that defy explanation through conventional physics. The consciousness detection algorithms provide quantitative evidence for goal-directed behavior that challenges our assumptions about the nature of intelligence in cosmic environments. The chemical composition and materials analysis reveal an object that appears to defy natural formation processes, while providing no definitive evidence of artificial manufacturing. The extreme carbon dioxide concentrations, unusual isotope ratios, and structural characteristics suggest either exotic natural environments we don't understand or advanced materials engineering that exceeds current human capabilities. The technological archaeology investigation identifies patterns consistent with billion-year-old artifacts while acknowledging the speculative nature of such interpretations. The scientific community's response to 3I Atlas demonstrates both the strengths and limitations of current methodology for analyzing genuinely anomalous phenomena. The conservative approach adopted by space agencies reflects appropriate scientific caution, while the reluctance to discuss extraordinary possibilities publicly illustrates institutional challenges in addressing observations that transcend conventional explanation frameworks. The tension between skepticism and openness to paradigm-shifting discoveries shapes ongoing investigation efforts. The interdisciplinary collaboration triggered by 3I Atlas establishes new methodologies for analyzing potentially artificial astronomical objects. The integration of artificial intelligence, analysis, consciousness detection protocols, technological archaeology, and message decoding techniques creates analytical frameworks that transcend traditional disciplinary boundaries. These methodological advances prepare humanity for future encounters with phenomena that challenge conventional scientific categories. The investigation reveals that distinguishing between natural and artificial phenomena becomes increasingly difficult as observations approach the limits of current theoretical understanding. The boundary between possible natural processes and conceivable artificial technology blurs when dealing with systems that operate on cosmic timescales and energy levels that exceed terrestrial experience. The 3I Atlas puzzle illustrates how extraordinary observations can expose the limitations of existing analytical frameworks. The implications of the 3I Atlas encounter extend far beyond immediate scientific questions to fundamental considerations about humanity's place in the cosmic community. If this ancient visitor represents natural phenomena, it demonstrates that the universe contains processes capable of creating apparent organization and complexity that mimics technological artifacts. If it represents genuine artificial construction, it establishes that intelligence and engineering capability can achieve permanence on billion-year timescales. The possibility that 3I Atlas carries information about galactic civilizations transforms our understanding of potential cosmic heritage. The message hypothesis suggests that advanced intelligences might create archives designed to preserve and share knowledge across cosmic timescales, making every interstellar encounter a potential opportunity for cultural and scientific exchange. The investigation establishes precedents for recognizing and responding to such communications, should they prove genuine. The departure of 3I Atlas leaves humanity with enhanced awareness of cosmic possibilities alongside frustrating uncertainty about this specific encounter. The object's passage through our solar system provides a template for recognizing similar phenomena while highlighting the analytical challenges inherent in studying visitors from unknown origins. The investigation creates both methodological advances and epistemological questions that will influence future astronomical research. The 3I Atlas encounter also demonstrates the importance of maintaining multiple analytical perspectives when confronting genuinely anomalous observations. The combination of skeptical analysis and speculative hypothesis generation provides complementary approaches for advancing understanding while avoiding premature conclusions. The investigation illustrates how extraordinary claims require extraordinary evidence, while acknowledging that extraordinary evidence sometimes accompanies genuinely extraordinary phenomena. Perhaps most significantly, the 3I Atlas investigation transforms our relationship with the cosmos, from passive observation to active engagement with the possibility of intelligence and engineering on galactic scales. The encounter prepares humanity for future interstellar visitors, while establishing analytical frameworks for recognizing phenomena that transcend current understanding. Whether we encountered natural processes or artificial intelligence, the investigation expands our conception of what's possible in the universe. The final lesson of 3I Atlas lies in recognizing that cosmic mysteries often resist simple resolution, instead opening new questions that drive continued investigation and theoretical development. The ancient visitor's passage through our solar system provides a reminder that the universe contains phenomena that exceed current understanding, while offering opportunities for discovery that challenge our deepest assumptions about intelligence, technology, and our place in the cosmic community. As 3I Atlas continues its billion-year journey toward distant stars, it carries with it whatever secrets remain locked within its mysterious structure. Humanity retains only observations, memories, and questions from 6 extraordinary months when the cosmos delivered a puzzle that expanded our understanding of what's possible among the stars. The investigation concludes with enhanced analytical capabilities, methodological advances, and profound appreciation for the cosmic mysteries that await future discovery.